everyone, welcome to Mastering Postgres, Scaling, Tuning, and Beyond Virtual Summit brought to you by the Armenia Postgres User Group. My name is Emma Soroyan. I'm the founder and organizer of Armenia PUG. We are the PG community in Armenia, a meetup group based in Yerevan. And today I'm going to be your host. So we're going to have 5 sessions and followed by Q&A, each followed by Q&A. Please mute yourselves and post your questions in the chat. Speakers will take the questions and answer them towards the end of the session. Harry from India, he's the founder of Open Source DB. His session is titled, All You Need is Distributed Postgres. So Harry, please start whenever you're ready.
Sure. I'm going to start sharing my screen and let me know when you see that. There you go. Can you see my screen?
Yes.
What do you see?
Yes, it's good.
Right, cool, sweet. Thank you everyone for joining this, and Emma, thank you so much for inviting me to be part of the virtual summit. Armenia PostgreSQL User Group is something I've been following and doing, and you've been doing a terrific job. Just a bit about myself, folks. Right, I've been doing databases for the past 19 years. That's the only thing I know. I don't know anything else. I am the founder of Open Source DB, which is a Postgres services company based out of Hyderabad, India. Postgres ecosystem is such a fantastic one that we were able to grab customers across the globe. We have had customers coming out of Australia, spanning till South Africa and the US and South America. Apart from Open Source DB, I am also working as a consultant at PG Edge, and I closely work with the DigitalOcean as a wavemaker, which is a program that is getting DigitalOcean closer to some of the users at a developer level, folks who are getting to know about the cloud modernization. And apart from the day-to-day job that pays my bills, I'm passionate about community building, just like Emma. I have founded Hyderabad Postgres User Group, WISAC, and another not-for-profit organization called as Postgres Women India. I've been a Code of Conduct Committee member at the Global Postgres Group and a code member of Postgres India group. I've been speaking at Postgres conferences for the past 6 to 8 years, I would say. And I also teach Postgres at some of the universities in India. And before even we get started with what we can do today, okay. Right, you guys hear me well?
Yes.
Okay, so before we get to the actual slide set and the topic that I wanted to discuss, right? This is a cool little fun that I wanted to start off with. This is probably me in step one, creating some messy routines, and we are going to be listening to a good friend of mine and a partner of ours, Dr. Luigi Nardi, who would not be so happy looking at this picture, but I still like to taunt him. This is the exact situation that I have been seeing a lot of folks. I have seen a lot of AI related mess that is happening. So for all the AI evangelists and folks, right, this is for you. And if you have to say something about it, please do say me in the private and not call me out on that one. This is the brief agenda that I have now. I won't do a lot of slides today. I will split my time in doing a detailed demo of how you will be able to set up a Postgres multi-master system. But before even we go to the demo and understand what is the actual software, what is the solution, how do we go about setting some stuff, I'd like to throw some light on the multi-master application for high availability. What would you do with respect to MMRs, with respect to setting up your solutions, setting up some of the Postgres clusters per se, right? And before even we go, take a look at this, right? Now, if I have to look at the theme of our whole talk today, right? So scalable Postgres isn't just a product, isn't just a database, isn't just a platform, right? In my honest opinion, it is a philosophy that we will have to look at, right? So scalability of Postgres, scalability of any of the forks that you are using at this point of time, consider it less as a product and more as a philosophy, and then you will be able to see a lot more success with the whole thing, I would say. And my goal for today will be to move some of our colleagues who have joined on this meetup, on this Zoom call, right? I'd like to move them from curiousness or the skepticism that they have with respect to multi-master systems, with respect to active-active replication, right? To an intrigued and a confident notion, right? Towards looking at how Spark extension can change that, right? How Spark extension can give you an architectural approach and the offerings like robust and practically implementable multi-master systems. Now, when you look at this diagram, when you look at this pictorial representation, we could see that the left-hand side, primary and the replicas that we have, this is the conventional setup that we have seen, right? Conventional setup that we have seen for a very, very long time. And on the right-hand side, you have multi-master cluster. One thing that keeps as a standout thingy for you, right? So multi-master replication is a database architecture. Now, if you look at it at a very, very high level and a 10,000 feet overview, right? It's a database architecture where multiple nodes can accept write requests, right? The application can go ahead and send out a request to multiple masters and ensuring the data consistency across the nodes that we have in place, right? So these are the three nodes that we are saying, right? You can create more nodes, but an ideal multi-master system would start with 3 nodes, right? It enables high availability. It enables, it makes sure a lot of fault-tolerant systems could be built, and it could also look at handling, concurrent data modifications that could happen, across your application stack, right? So that's the multi-master replication, kind of a very high-level thing that I will throw at you, and we'll go through some of the design aspects that we have in place, right? Some of the design principles that we have seen, right? So if you look at some of the design principles that we have seen here, right? So two-phase commit, right? Two-phase commit for me is coordinator sends a prepared statement, right? To all the participants before even committing any transaction to your database, right? So all the participants respond okay, and the commit is, and once the whole transaction is committed, that's where you'll see the entire data available on all the nodes, right? So the only drawback with the two-phase commit, or two-phase that we call it, right, is blocking, and if the coordinator crashes midway, right? So it's possible, right? The entire participation chain cannot proceed anywhere, right? So while we are looking at some of these principles, right, raft consensus has been there for a very long time, right? Some of the patronage, some of the rep MGRs, the single master systems that we have built use raft a lot, and it's a leader-based consensus, right? Now, if you look at the conflict resolution strategies that we have in place, right? So the last writer wins is something that we would want to be as the baseline, right? So the last timestamped right is chosen as the winner of the whole transaction, right? If there is a kind of a conflict that we have in place, right? So I'm putting this premise at the back of your minds because we are going to be looking at a solution which has solved some of these principles. We looked at we are going to be looking at some of the pieces that has already been sorted out by the Spock extension, right? Now you could take a look at the application specific rules. I know in most of the BFSI domains that we have seen, right? It is more of, hey, do you have to commit your transactions only on node 1, because node 1 is considered to be the primary node, and the node 2 and node 3 are the n number of nodes that we have set up, right? If the application has any specific rules, or you might have have a quorum-based commit also, right? So if you look at some of these principles, right, these are the building blocks for us to build, for that matter, any replication system, right? Whether it is a single master or a multi-master and an active-active cluster. And pack theorem is something that we have seen a lot, right? Whenever you look at an active-active system, we tend to look at, hey, what is that you would offer, right? Whether it is the consistency, whether it is the availability, whether it is the partition tolerance, right? So you would look at your solution with an automatic failover in place, that you are able to shard your workload, you are able to shard your processing, and able to load balance the whole solution per se, right? So this is to touch upon some of the principles that the whole replication ecosystem has seen, right? Now, if you go take a look at some of the considerations, right, the important considerations for you to even take a look at distributed databases, for you to take a look at, hey, am I there yet to envisage on the MMR ecosystem, right? Am I there yet from an application standpoint, from a database topology standpoint, right? So some of the things that bring to the application or the DBA's knowledge is, does all the tables have primary key, right? The reason why we need primary key is all the logical transactions, the logical replication happens on primary key, right? If you do not have one, you will have to rely on something called as replica identity full, which we all know is a seriously costly affair, right? And the database workload that you are working, right, of the application throwing at some of the workloads, right? Is that conflict free, right? When you say, is that conflict free, right? Are there any two processes that are going to go ahead and update the same row at any point of time, right? Do the nodes or the application and node silo are going to be talking to each other and generate conflicts, right? Is there a possibility that you will have to make some transactions synchronous, as in, hey, I am going to update the credit score of mine, which is going to have ripple effects on how my whole financial footprint is taken a look at, right? So some of the transactions needs to be synchronous. These are some of the application related aspects you would take a look at and say, hey, does it even make sense for us to look at a distributed databases, right? Does it even take a look at some of the solutions that we have available in the market, right? Now, another important uh, 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 component that I keep looking at is now how much of FOSS versus cost versus the cards that we have in place, right? FOSS obviously is the fully open source, and cost is commercially available open source, right? And cards is something like an Oracle, Golden Gate, or something like commercial off-the-shelf software, right? And if you are already on Postgres, I don't know, we are in a Postgres meetup per se. I don't know if you are already in a Postgres, do you think the tagline compatibility, right? So some of the software that I could take a look at is probably the Yugabytes, the Cockroach DBs, which are compatible. But do you look at those solutions, or if you have already built your applications for Postgres database, right? Do you want to do a massive lift and shift of your workload, application workload, and still be in the Postgres ecosystem and have an extension-based MMR system, right? So these are some of the considerations that I would say when we look at, hey, I am going to be looking at an MMR slash distributed systems in place. Now, these are some of the things that you would definitely look at, right? So these are some of the things where you would see, hey, I have conflict resolution available with the PG logical extension, right? I could take a look at eventual versus strong consistency. If somebody says I can do I can live with eventual consistency, but I would need availability or high availability as the major offering, that I would look at a solution, right? So that's when you would look at multi-master or a high available solution, right? When you are looking at replication latencies, this is something that you will have to look at. I mean, this is something that we have been living in for a very, very long time, right? So it could be a network delay. It could be because of somebody grabbing an exclusive lock on some of the objects where you are performing transactions, right? And performance overhead that comes with your synchronization, meaning you are generating a transaction and waiting for that entire gamut of things where, hey, I am sending across a connection request, doing a write operation, making sure the standby is also receiving the transaction, right? It gets committed on the standby first and then it gets an acknowledgement, right? That is another performance overhead that we take a look at while we are designing our multi-master systems, right? Now, topology complexity is another thing, right? Now, where you will look at observability matters, as you would look at monitoring of the systems, you would look at automatically generating some of the add node capabilities, right? Automatically adding the nodes that are failing as part and parcel of your cluster, right? These are some of the complexities that you should also be cognizant about while you are designing some of the MMR solutions and distributed this. Now, if you see, right, if you are successful in designing some of these aspects, taking care of some of these nitty-gritties, right? You would look at, hey, what could be some of the best practices that we would take a look at, right? What should be some of the best practices that the solution should offer, the Postgres-based extensions should offer, right? I would say these 4 points are something that I've been, experiencing in a lot of customer interactions and, in our own, way of articulating a strong, active distributed postal system, right? Now we should look at what is the trade-off between the consistency and availability, right? Now, obviously, you would look at something like, hey, do I have to make sure my entire systems are available, like 3 nines, 4 nines? People talk about 5 nines of availability also, right? Do I have to be worried about those nines of availability, or make sure the application has a consistent data to play with? You would look at a replication-based model, right? In a database system where your use case is just to make sure the database is consistent. I do not care about the latency that I am going through, or I am going to encounter. I am not worried about the availability, right? I don't know who would say that I'm not going to be worried about database availability, right? So you should look at the right replication model on a different use cases, right? Some of the use cases that I would see right now, I would be looking at a couple of use cases where we have looked at a customer's problem, and then we are going to be talking about what are some of the practices that we have seen, right? What are some of the solutions that we have given them, right? And the monitoring and observability is something that is not compromised with any aspect per se, right? So you should look at monitoring of the data. You should look at what is the exact replication between your active nodes. How are they doing, right? How you will look at it. Now, if I summarize the last 12 to 15 minutes of what we have in place, right? So I would say, what are some of the problems we have, right? We have topologies complexity, right? We are in a slightly not so very comfortable position where we cannot say whether it is consistency, whether it is availability, whether it is the latency that is our massive driving factor, or we look at some of the conflict resolutions that we have in place, right? If some of you who have looked at BDR, or looked at some of the active and distributed systems, and then say, hey, I have looked at this system, I am not happy with it, and I'm not going to touch this multi-master or active systems anywhere in the near future, right? If you have had any of those experiences, please do let us know on the chat. I would love to know what was your experience. Now, moving on, now what makes the PGH slightly different from some of the other pieces that we have in place, right? PGH platform is a open source software that is available on Git, right? The Spark extension is available for you to download, and github.com has the entire code, right? Now, what makes PGH slightly different, right? So they just took what worked in Postgres, right, with respect to the logical replication, with respect to the BDR extension that was available before, with some of the popular extensions like PG Logical, right? So whatever that worked in Postgres was now consumed and then made sure it is created as a Spark extension, and we went ahead and added conflict resolution, right? Conflict avoidance with the delta columns in place, right? We looked at the data sovereignty with respect to the locality, right? Locality awareness, and the data governance piece of it, right? And to tie all of these things together, we have got one CLI piece, right? CLI for Spark that takes care of, hey, how do I provision some of the active systems, active distributed Postgres systems, right? The CLI piece is another thing that we will take a look at. Apart from that, this is all built on a standard Postgres engine, so you are not going to be doing any changes to the database, the ecosystem per se, right? If you have been working on PG 14s or 15s or 16s, or the latest 7 days, you don't change anything, right? You make sure Spark is compiled, and then start leveraging some of the active stuff we have in place. Now, there are two more extensions that I would like to throw some light on, right? The Snowflake and the LOLOR extensions. Snowflake is something where you have unique Snowflake sequences that are available for us to play with, right? So in an active system and a distributed system, you will not be able to work with native sequences because there is a chance of duplicate IDs that gets created. So Snowflake will give you that uniqueness. Again, this is another Postgres licensed software, so which means that you can take a good hard look at it and start using it with or without Spark, with or without PGH, right? You'll be able to go download the Snowflake. Same case goes with LOLOR. That is another extension where we have seen the traditional logical replication we have available does not support the replication of large objects. Now you could ask a question of, hey, who is creating any of these schemas with LOLOR, I mean, with OID or data type, right? There are a few systems that are still there. Some systems in the healthcare sector that are still using OID, thanks to some of the external integrations that they have, right? One of them that I keep bumping into is the FHIR, Fast Health Interoperability Engine, with respect to Happy APIs, right? So that's another product which is very widely used in the healthcare sector that still uses the OIDs as the data types while they are creating a Postgres system in place. Now, apart from that, PGH supports a lot of other extensions. I don't want to spend more time on this, but let's just go a little into the Spark and dig in and say, hey, what does Spark offer us? Right? So Spark's core idea is just to make sure the asynchronous multi-active replication. I don't know how many ever nodes that you create, you are able to make sure, right? There are replication sets, there are subscriptions that are created. There's that low-level infrastructure that Spark creates, right? And it has got apply workers, the supervisors, and the manager processes that is going to make sure the whole things are and then the trains are running on time, right? So that's the core part of the Spark's idea, right? Over and above Spark, right? Now you would want to see, hey, I would like to see conflict resolution out of box, right? I would like to see conflict resolution. If there is a conflict that has been erased, do I have enough observability matrices available where I could say, hey, what is the exact conflict that has erased? Who is the node that has erased the conflict? How are we going to resolve some of the conflicts, right? Spark has inbuilt conflict resolution aspects, which makes sure, again, the last writer wins model is something that we have seen. And as part and parcel of Spark's database schema, right? The extension schema. So you have got conflict underscore trackers. So you've got resolutions, Spark.resolutions table, which gives you all the monitoring data and makes sure in case in case there is a conflict in place, right? How do you make sure those conflicts are tracked and how they're resolved in the due course of your logical replication? And another important piece is the ACE, the anti-chaos engine that we have made available with Spark. So because we are talking about multiple nodes, because we are talking about multiple application and data sets working in tandem. So you need to have one worker process. You need to have one sanity check process that makes sure, hey, the data between the nodes is all in sync or not, right? The ACE is the anti-chaos engine that makes sure the databases remain in sync, right? Now, data residency has been pretty much a de facto option that people have been seeing for a while, right? So Spark has inbuilt PII compatibility, right? Now, the PII residency rules that it has made available, right? So local governance of the database. So you will be able to go ahead and say, one partition of the data lies in one region of your AWS when you are provisioning, and then you will be able to go ahead and have another partition of another country, or you could do the local governance of the entire data set in by out of box Spock PII replication model, right? This is where you will be able to do row level logical replication, column level logical replication, and the ID based mechanism that we have seen, right? Now, we did say that with Spock, there is also something called as a CLI for Spock, right? So again, this is another command line interface where you could simply go take a look at once the PGH installation run, which we are going to see in a moment, has the not necessary commands for us, right? These are some of the commands that a nuts and bolts engineer like me would love to work with, right? So this is to make sure whether my cluster is having the right data set or not. Am I able to go ahead and make sure my clusters are in sync with each other? How do I call the cluster module to make sure the configuration, right? The one-time configuration that I do for the entire setup is as easily provisioned and orchestrated as possible, right? These are some of the modules that are available with CLI, which helps us to make sure the Spock extension, the Postgres minor versions and major version upgrades are possible, right? The UM is the update manager, which takes care of how your upgrades are handled, right? And how you can do some of the cluster level activities like adding a node, removing a node of your cluster and stuff, right? So all of these are part and parcel of the CLI that we have in place, right? Now, I'm going to pause here and see if there are any questions that we have on the chat up until now. Right, cool, sweet. No questions up until now. Let's jump on to the couple of use cases of the customer cases that we have solved with the active replication and Spock, right? So the one challenge that we have seen is my high availability of the databases, or the 4 nines availability of it, right? And at any point of time, you look at the database not being available, or your application does not have a database to work with, or to write to, right? It has caused a lot of grievance, a lot of issues for a lot of DBAs, right? So this is just a simple case between a customer asking for two important, raising two important challenges, right? I would like to see high available database system, and if there is a downtime, I should be in a position to get out of that downtime ASAP, right? Now the solution with the brief time that we have spent with the whole explanation with respect to our systems, right? We've seen that multi-master system could be a great way to look at, hey, at any point of time, if there is one node that is down, there is another node that is already available to take the load for the application, right? Provided you have the connection concentration layer talking to all of these multi-master systems in place, right? Now, there are two pieces that got out of it, right? So we could take a look at the outcome with as close to 4 nines uptime as possible, right? With no single point of failure, right? That's what we call it as ultra high availability, and with the data integrity point of time, right? So with respect to the ACE functionality, with respect to some of the CLI functionalities and modules we have in place, we were able to make sure the database is in sync. The table data that is there, available in the tables are in sync, right? And then from a scalability standpoint, right, you are able to go ahead and see how much of scalability you can achieve, right? Provided you have got as many number of nodes as possible. That is something that we could look at it, right? So essentially what we say with these is it's not the the databases that are going to be in a mundane fashion, or you will be able to set up these single masters and stuff. But you would look at a good tooling. You'll be able to make sure the databases are available in this. Now, the second use case is more of the challenge where we were looking at, hey, do I have to stick to one cloud service provider? There is a concept called as cloud concentration risk, right? So, so the biggest risk that I see is looking at some of the database scalability aspects that you would see. You would see that if you are not considering multiple clouds, or if you are looking at a single region or a single cloud provider, right? There are chances or bigger risks in in the recent times that we have seen, where a cloud's availability zone is not available, a region of a specific cloud is not available, and the database was down for a few minutes to seconds, right, which caused some of the issues, right? Again, we are looking at the same solution. I just wanted to make sure you guys have that at the back of your mind when we are looking at an active replication solutions, right? Now I'm going to go ahead and see, we can stop it and see if there are any questions, or go about going my demo.
There aren't any.
All right. Let me know when you guys see my screen, which is a command prompt. Yeah. So essentially what we are going to be doing here is, I've got two EC2 instances available, right? I've got two database nodes that got created, and then this is the Python script that you would require. That's all, right? This is the single command where you would be able to go download the install.py and then make a call and make sure you are installing the PG Edge latest and greatest, right? PG Edge has got different repositories available, one being a download, another being a devel, and then there day-to-day ops that happen. So essentially what we are doing is we are just trigger that Python script, and we are doing a download of the latest and greatest PGH Spark code, the Postgres source code based installation, and we are also installing the PGH CLI, which is required for us to go about setting up the PGH for us, right? So this PGH is more of a, you take a look at the command here, PGH info, which helps in making sure what is the exact node you are on, what is the configuration, what is the operating system you are on, just to give a snippet of how the whole database node is looking at while we are running. And this repository is where we are downloading the PGH software from. Again, this is an open source thing that we are seeing here. Let me go ahead and play this. And then I'm doing the same thing on node 2 also. So there are quite a few ways of installing PGH and two nodes here. The chosen option for today, for the sake of demonstration, is I've looked at how do I make sure I showcase a lot of CLI pieces to you, right? How do I make sure I tie a story, stitch a story around what are some of the moving parts of the active configuration or active replication in place, right? Now, this piece, what we are seeing is we have downloaded the software, we install the CLI, and now we are looking at both the nodes are available. Now, this piece is where we are installing the PG17. So essentially, this is a source code that we have compiled of PostgreSQL.org downloads. And we are now setting up the latest and greatest 17.5 on both the nodes. So if you look at it now, the Postgres, while we are installing, right, there is also another configuration and initialization phase that happens, right? So the command is the pgh init 17. So this is the initialization for us to go ahead and say, hey, what is the credentials that you would use? I know what are all some of the pieces that you would do of it, right? Whether you are doing an init DB on the node or not, right? How the init DB is going to work, right? So we have initialized the whole software on both the node 1 and node 2. Now we are going ahead and installing the Spock, right? The extension where which is responsible in making sure all the active replication is taken care, right? Now take a look at the extension, right? So some of the prerequisites that the database extension Spark would require, right? Obviously, the wall level set to logical. This has been there for a very long time, right? So logical is when you will be able to do logical decoding between one publication to a subscription. In this case, with Spark active, all of the nodes will have subscriptions created amongst themselves. Now, let me fast forward. And then there is also this Snowflake extension that I spoke about, right? The Snowflake extension is the one which will generate the unique ID values, which can be used as your primary key, right? Now, if you take a look at it, right, you are taking a simple create extension command on our screen, right? So we install Spark, we have installed Snowflake, and then we are also going about doing the same thing on these two nodes. Now, this is to make sure I create my environment in place and then log into the Postgres cluster and see what is the database that I have created, right? So this is the three extensions that we have. PLBGSQL is a default one. Spark and Snowflake are the latest extensions that got added to this thing. Right, and now I am going ahead with the actual infrastructure that we are creating for the replication model, right? So we said that you can create as many nodes as possible, but for us to get started for today, I've created 2 nodes, right? So the infrastructure that the whole Spark would require is, hey, you have got Spark node, and then you have got replication sets, and then you have got subscriptions, right? So these are the 3 moving parts that you would require to create a multi-master replication between node 1 and node 2. Essentially, what we will do is we'll create the node on both the VMs and make sure they are cross-wired and then they are talking to each other. That's how the whole node creation and stuff happens. So you would create the node, and this is the node 1. If you take a look at, there is a node identifier that got created. Now I'm doing the node 1. Node 2 is also created. If you see the node creation, right? So it's a simple command where we are giving the DSN. The DSN is what is the exact node DSN we are going to have, right? And then this is the subscription that we are creating. Look at the IP change between them, right? So we are creating a sub N1 to N2, which is going to broadcast all the changes of your N1 to N2. And then, it is going to use the DSN of your N2 server, right? So 172.31.25.225 is the IP address of your N2, right? The same thing will happen on the N2 also, right? So you will create the N2 to N1. So this is the N2. So this is the IP address of my node 1. And boom, right? Now I am going ahead and my whole infrastructure is created. I have the whole system that is going to be working on, hey, what are the metadata tables that I have in place, right? So the metadata with respect to what is a Spark node, right? Spark has its own schema that got created, right? Nodes is one of the table, right? You've got subscriptions. the general, similar to PG underscore catalog schema, Spock also has a bunch of tables and views, which helps us in tracking the whole system schema. Right? So you've got Spock subscriptions, you've got the nodes. So these are the two components that will make sure we are able to go between these N1 and N2. In the interest of time, I'm going to go ahead and see, right. So this is another important piece where I want to touch upon, right? So the conventional logical replication systems that we have seen, right? The automatic DDL replication is something which has been missing for a bit of time, right? So with the with the Spark extension in place, it actually enables the DDL replication, which means if you do any DDLs on N1, all of them will be transported and broadcasted to N2 and vice versa, right? This is controlled via some of the GUCs that are available, which is part and parcel of this POC, right? Enable DDL replication is one amongst them, where if you go ahead and enable, you will be able to make sure that all the auto DDL or the automatic DDL pieces that you are going to be doing is replicated onto the second node easily. Good. And then these are the other GUCs in place, right? There are three GUCs that I mentioned about: enable DDL replication, include DDL rep sets, and enable the functions of it. Allow DDL from functions. Once these pieces are done, you'll be able to, again, these are the GUCs that require only a SIOP signal to the database, which means you don't have to disrupt any of the database availability per se. And boom, once the auto DDL is on, you will be able to create the table on the T1 and see that the table is available on the second node, right? I'm switching between the N1 and N2, and the database where you are creating tables and the data that is in sync is also seen here. Right, the update is happening in node 1 and it is available on node 2 at this point. Right, Emma, how are we doing on the timing? I know I was supposed to close by 5:45 and we are at 5:50, I believe.
Yeah, if you finished, there are two questions for you here in the chat.
I'm going to take a look at them. Hi, Himanshu. In active HA cluster for simultaneous, we have an offset and the increments is not sequential. That's why you would use the Snowflake sequences framework, Himanshu, to get away from that offset and the increments. So you will be able to generate non-duplicate primary keys and then assign it to your databases, your database tables. And is PGH compatible with AI frameworks, and which ones are the most used? PG vector, vectorize, till PG ML was there in the existence. All of those AI frameworks were compatible with PGH. There are customers who are using them in production at this point of time. They are supported, yes, Python based too. Cheers.
Thanks a lot, Harry. Second speaker is Joseph. He's a Postgres specialist, and his talk is titled Postgres Connections, Memory Usage, Linux, How Much, Why, and When. Welcome, Joseph.
Yeah, thank you very much, Emma, for inviting me here into this conference. Emphasize that you probably know Simon Riggs. In his last speech on the European conference in Prague in 2023, he actually mentioned that from his perspective, we need more of these online conferences. So Emma, you are doing great work. Keep doing it. And hopefully there will be more of these conferences. And he also mentioned that we shall keep asking even seemingly stupid questions. And these questions regarding memory usage, I think they must look like very stupid ones because we all know Postgres uses so much memory. There is workmem and all this stuff. But I actually discovered that things are not that simple. So hopefully you see my slides and let's dive into it. I connected from Berlin, Germany, and I work here for German company Credative, which offers support for open source products, including Postgres, which is our biggest topic. And I have more than 30 years of experience with many different databases. I'm originally from Czechia, now living in Berlin, and I already talked on different conferences about different topics. So here is what I want to show you, and I created some AI-generated pictures to make these slides less boring. So let's dive into it. Linux memory management. I actually discovered when we want to understand how much memory Postgres uses, we need first to make sure that we all are the same page regarding Linux memory management. We all generally know that there is this concept of physical memory in the computer and this virtual memory giving virtually to the process and only some parts of virtual memory being really physically mapped to the existing physical memory. There is this memory management unit, like a piece of hardware, which does these allocations. And on Linux, on 64-bit architecture, it uses pages of 4 kilobytes, 2 megabytes, or 1 gigabyte. There is something like translation look-aside buffer, which speeds up the access to the memory. Those 4 kilobyte pages, there have been historically chosen when hardware was very small, and in these days they pose actually a big overhead when they should be managed. Therefore, we have these huge pages, 2 megabytes or 1 gigabyte, which are internal feature of memory management unit done in hardware way. And they can save a lot of space in that transaction look-aside buffer. But problem with those huge pages is they cannot be swapped out. Only those small 4 kilobyte pages can be swapped out. There is also a concept of transparent huge pages, which is feature of Linux kernel, and kernel can automatically reallocate many small pages into a huge one or back again. But Postgres documentation still warns that these transparent huge pages are known to cause performance degradation. Yeah, well, on modern hardware, it's maybe not that critical, but not everyone has hardware up to date. So recommendation is to use explicit huge pages. There is this setting, huge pages and huge pages size. And we can say try or on or off. If we say try, Postgres tries, but if it does not work, it does not use them. If we say on explicitly, it can block postmaster from starting if it does not work. And there is also in Postgres 17 a huge pages status read-only parameter, which tells us if we are using those huge pages or not. On modern architecture, we have also this non-uniform memory access, meaning memory is divided into different banks for different CPUs, because otherwise one memory bus would be the worst bottleneck in the hardware. And Postgres 18 got some initial support for NUMA awareness. So hopefully we will see huge improvements here in the way how Postgres uses different banks of memory. When we allocate memory on Postgres, we have these 4 different stages. First, unallocated memory. Second, allocated but not mapped to main physical memory. Third is allocated and mapped to physical memory. And fourth is allocated but swapped away to the swap space. There are some names like page fault, major page fault, but what is important to understand these 4 stages of memory allocation. We also talk about anonymous memory and file-back memory. And anonymous memory is not associated with any file, can be swapped out, but cannot be reclaimed by operational system because it's unique. Those data exist only in memory. On the other hand, if we have filed back memory, this is associated with some file on the disk, and therefore it can be reclaimed by OS because we can read again that information. So here is some schema which shows this anonymous, filed back, private, shared memory, how they actually fit together. And based on these stages of allocation, we of course have those different values. And here I found out that there are some misconceptions, so I want to dive slightly deeper here. So if we allocate memory at the beginning of when process starts, we allocate it only as virtual memory, which means that at the very beginning, we get from memory management unit information that memory was allocated, but it exists only virtually. So this is that virtual memory size, which is reported by many commands. But only that part which is later physically touched by process is physically allocated using in that physical memory, and therefore it resides in memory, and we now say that this is resident set size, meaning amount of physical memory really used by that process. And this thing is slightly complicated because there could be shared libraries which are referenced by that code, and those shared libraries must be also loaded into memory. Advantage is if we have many processes using the same shared library, then this shared library is loaded into memory only once and reused for all those other processes. So if we take aside this shared libraries size, we have actual memory size, which is really unique to that specific process. And here we say that it's unique set size. Regarding that shared memory, there are 2 things. We have shared memory for sharing a large amount of data between processes, and this is what Postgres uses for running parallel workers. Or we have these shared libraries, which are actually loaded for running code in those processes, and this, of course, Postgres also uses with every session. We have also this concept of memory overcommitment. We can allow a machine to allocate more memory than it physically uses, because idea is that not all processes will use all memory all the time. But for our purposes, this is not important right now. With overcommitment, we also have this out-of-memory killer, and for our understanding, it's necessary to understand that from Postgres processes, only postmaster is the most important one. Therefore, it adjusts its score for out-of-memory killer to lowest possible amount, so it is not killed by out-of-memory killer, because we sacrifice connections, but we must keep postmaster running, because postmaster will restart everything. Yeah, we can talk about swap, but not today. And let's jump on how to measure memory usage. So we have some well-known commands. We all know them, or maybe we think to know them. So let's dive into them. First of them is this free command, which can also show us memory overcommitment. Yeah, well, those are nice numbers, but they cannot help us if we want to see one process. And usual program when we go to see memory used by one process is stop command or its variants like htop. all these commands, they still show the same. They show us virtual memory, resident memory size, and shared memory, which works nicely for normal processes, but it's actually a bit problematic for Postgres connections, and I will show it on examples. We also have this pgtop command, but it generally shows exactly the same. So no added value here. Only this smem command can show us this unique set size and also value which is called proportional set size, which means it's unique set size plus portion of shared memory of those shared libraries. Because if we would have 10 processes using the same shared library, we can say that in average, 1/10 of that shared library could be added to each of those processes to somehow show that it is not used fully. But we are interested mainly in this unique set size. Unfortunately, this command is not exactly nicely formatted, but at least it shows these values. But for our purposes to understand how much memory is really used by Postgres connection, we must dig into Prost's file system. And there is this meminfo or status for each process ID, but mainly this smaps for each process ID. And this smaps file is quite huge. It contains sections like this one, starting with the header showing memory region, start and end address, permissions, path to the file, and different values for that memory region. So only here we could find real answers for how much memory Postgres really uses in the connections. But before we dive to it, let's talk about memory objects which are important in the scope of this talk. So we have these shared buffers. Everyone talks about shared buffers, and it was seen as like very important setting for Postgres. Yeah, it's true. Usual recommendation is 25% of available memory. We have also this PG shared buffer cache extension, which can monitor usage of shared buffers. But what is important for us to understand in this context is when Postgres starts, those shared buffers are first allocated only as a virtual memory. They are not physically in memory. They don't use that amount of physical memory. Only a few kilobytes somewhere, but otherwise, when Postgres starts freshly, they are empty and therefore exist only virtually. I will skip this. And beside of shared buffers, we have other shared objects which are created on start of the Postgres. And here I must emphasize especially these simple, least recently used buffers, SLRUs. There have been huge development for the new version. We see better information about those buffers. And if we look into PG settings, we see this shared memory size, read-only parameter, which will show us total size of shared buffers plus size of these shared objects, which are we can change settings of this change size of these shared objects, changing some settings, but they always require restart because they are allocated on the startup. And with this understanding, let's look at how much memory Postgres connection really uses. What we need to understand, and what we all know, and some people don't like, is that each connection in Postgres is actually independent process in Linux. It has its advantages. It has its own isolated memory, and it is great for stability and security, but it is also very resource intensive. So these processes have been chosen for higher stability in 1990s before reliable threads were implemented into Linux. Those threads now are considered much more stable and lightweight, so there is some ongoing discussion about switching Postgres into threads. So let's check how much memory Postgres really uses. If it is true that the workmem is so important to understand this and what we can find. I use testing machine with 32 gigs of memory, Postgres 17, shared buffer set to 8 gigabytes, and workmem 64 megabytes. Why 64? To have some nice number which is easy to find in those memory outputs. So I started Postgres, started first connection, and I can immediately see that virtual memory is like this whole size of shared buffers plus shared objects, but resident set size is only like 20 megabytes. So here we see first results. It's not true what some people say that workmem is immediately allocated and when connection starts. It's not true. It allocates less amount of memory than this huge workmem. If we would have small workmem, it would not be that visible, but with bigger workmem, we can immediately see it. And now let's dive into those S-maps to understand which values we can find here. And here is summarization of those memory regions from S-maps. And here we can see that here is binary of Postgres. There is some memory anonymous without link to any file. Here we have heap. Here are two shared memory segments which each connection uses. Here are shared libraries which are actually used by every connection, and here we have this very interesting line which starts with /dev/0 in parentheses deleted, and here that size, that virtual size, tells us that those are actually shared buffers. One guy explained to me how these things are actually connected with linked to connection, and why there is this strange string which is actually like sort of placeholder for telling that those are shared buffers. But I must dig deeper into this, why it is so exactly. But what we need to understand is that this line represents shared buffers which are connected with that session. Then I used some nice query. I used table with JSONB toasted data. Table had 38 gigabytes of memory, so it's not fitting into memory. It's not fitting into shared buffers. And I switched off parallelism. Why, I will explain later. And when we execute this, we can see in top command immediately that resident set size is 8 gigabytes, shared memory also 8 gigabytes. We can also see these values if we list them using Python code psutil full memory full info. And now clients are actually surprised. Does it mean that one connection uses really 8 gigabytes of memory? So let's dig further. If I now summarize data for this one connection from S-maps after that query was done, I can see really those horrible total numbers, but here is this line for those shared buffers, and here I can see that those horrible numbers come all from shared buffers. It's not memory physically allocated for that one connection, because you can see that these resident set size and proportional set size, they're actually still small. Only horrible numbers are in this line for shared buffers. So I made some other tests. I switched now parallelism on. I allowed 4 parallel workers, and I ran the same query. It started additional 3 workers. And when query was running, I could see those additional sessions, each with different size of this residual memory, resident set size. And when it ended, only that main session remained, which started those parallel workers, and it remained with a much smaller amount of resident set size. Seemingly, it did not use so much memory, but again, when we now summarize data from SMAPs, we see that again this horrible memory size comes from shared buffers attached to that session. And why it is smaller? Because another parts of shared buffers have been attached to those parallel workers, and they were deallocated after they ended. So only part of those shared buffers, which was really processed by this main connection, remained attached to this connection. And again, you can see these numbers, these other numbers are quite small. But when we look into top command, we see that first connection used, oh, horrible 8 gigabytes. Second connection was somehow better. It used only like 4.7 gigabytes. Why? Yeah, why? Because those are those discrepancies with shared buffers. If we try it again, we will get again interesting results. And now, after some tests, I have 5 connections, which I tested sometimes with parallelism, sometimes without parallelism. They all together give these horrible numbers, and clients are now asking, does it mean that my server is dying? Does it mean that it uses so much memory, which actually exceeds physical memory? Yeah, well, let's look into those SMAPs files. So if I simply summarize SMAPs files for all those 5 connections, I really get these terrible, horrible numbers, and it's critical. You know, this is more memory than I have. But if I take away that line which actually represents shared buffers, I suddenly see completely different values. You can see that first connection uses something like 4 megabyte memory without shared buffers. Second connection, only 3.7. This one uses more because in some cases workmem is allocated after it ends. I will explain in another chapter. But those other connections, they also use like 19 megabytes of memory, 11 megabytes of memory. So nothing like these horrible numbers you can see in top command. Actual memory usage of Postgres connection is actually very, very small. But this is unfortunate thing with that top command. It is built for different use cases, and therefore this allocation of shared buffers actually spoils those results. So we would need tool which would be also able to show this resident set size without those shared buffers, and only here we would be able to see real memory usage by each connection. So this was like still top overview, and now comes the question, okay, this is nice, but where is workman actually hidden in this? We are taught by many articles that workman is the most important setting, and we can calculate memory usage using workman. So where it is hidden? Because in those results, as you can see, except for this one number in one of those connections, there is nothing like 64 megabytes of allocation. So to understand it, I created some, I used some query which runs slowly enough to be able to measure it. I used JSONB data from GitHub historical events, which I used in my research about JSONB data and its indexes. And this table of 38 gigabytes with this quite simple aggregation query gave me the opportunity to measure memory usage of all those paths. And as I showed here in this summarization of SMAPs, there are different paths, different libraries, different types of memory, including this anonymous and heap. So when I gathered data, scraping data repeatedly during run of that query, and plotted this grid of those different paths from SMAPs, you can see that majority of those graphs are very boring, very flat, except for these three. So let's look at these three graphs deeper. That last one, those are our shared buffers. They just jump up and stay there. So we can take away this. But we have here these two other paths. One of them is anonymous memory, and second is heap memory. And here we see some interesting things happening. So when I plot better graphs, I can immediately see dependencies on workmem. I will recall that workmem is 64 megabytes. We have shared buffers 8 gigs. The table does not fit into memory. And here you can see graph which shows in one graph that anonymous and heap memory. Anonymous memory is plotted in blue, heap memory is plotted in red. And here there is summarization of those two parts of memory. And here, unfortunately, it's probably not that well visible. Here we have that workmem, 64 megabytes. And we can immediately see that anonymous memory is allocated in those 4 megabytes steps, because it's allocated always like those small data pages. But at the beginning, allocation exceeds workmem. And if we look here at those values here, we can see that it roughly allocates 1.7 times more than is workmem. And if we now add this heap memory into it and look at this summarization graph, we see this behavior of anonymous memory and heap memory. And sure enough, anonymous memory after this first peak stays more or less on workmem, but this heap memory allocates additional memory, additional on the top of workmem. So we here reach this 1.7 times more allocation of memory than is workmem. We can immediately see that it does not fit what we can read in many articles, that workmem is like most important setting. Workmem is sort of very soft setting. It can be exceeded, and it is often exceeded. And I did the same measurements for different values of workmem, and I've got very different behavior of that anonymous memory and heap memory. General rule is that with higher workmem, more things are happening in anonymous memory and less things are happening in heap memory. Because with workmem equals 8 megabytes, that heap memory exceeds on its own this workmem. But later with more workmem, it is going down and down. But as you can see in these results, and here are these peaks of different processing moments. In all those cases, when we put together anonymous memory and heap memory, we always exceed workmem. Like here, 2.2 times. Yeah, well, it may not look critical because we have 8 megabytes workmem, so we allocate like 17.5 megabytes of resident size memory for this particular case. But imagine situation when you have max connection setting calculated based on these articles which say that you can actually approximate this max connection based on available memory divided by workmem. So if you would have like 1,000 connections, which each of them exceeds actually this workmem and allocates 2.2 times more than workmem setting, yeah, it could mean difficult memory problems just because we believed that workmem is actually some limit which we can take into consideration. So in all these cases, workmem was exceeded, and it had also influence on speed of processing. So with smaller workmem, generally processing was much slower. With higher workmem, was quicker. But in these cases, we have the situation that it used external merge on disk. So there was some additional issue. There was some additional problem that that external merge did not fit into memory. So if I test it with higher workmems, I see different behavior that it's not exceeded that much. And here with workmem like half a gigabyte, it even processed everything in memory. So everything was fitting into memory. And as you can see, characteristic of this processing was quite different. And there was just one steep calculation, not these jumps as we can see on those other settings. So in some cases, quite extreme workmem set for that one connection and one query only can actually help you a lot because those things are processed much quicker and much straightforward in memory. What about parallelism? If I allowed parallelism, I will get parallel workers, and each of these parallel workers will, of course, allocate its own anonymous and heap memory. Here I allowed 8 parallel workers per gather, meaning that main connection started 7 workers, and each process allocated its own memory. And here you can see all those workers, their anonymous memory in blue and their heap memory in red. Here are boundaries when those parallel workers started and ended. And when we actually put everything together, we can see that that workmem was in total used 16 times. So we had 8 connections, and in total it used 16 workmem. So each of those connections actually used 2 times workmem. And this is something which we need to keep in mind, that things are not that simple. Here you can later, I will share those slides, of course. You can later look at the different settings of workmem with parallelism. And as bonus, I want to show you query with 2 order by clauses, which is like special thing. You would never do this. I understand it, but it shows nicely some behavior. So I put order by into common table expression here, first order by, and second order by here in the main query. So when I run this without parallelism, you can now see that it behaves differently, and this one query used 2.8 times workmem setting. So with some, I would say, crazy constructs in queries, we can increase memory usage when query is processed, when this anonymous and heap memory are being used by connection for processing memory. So with some of these crazy constructs, we can increase it even higher without expecting it. Simply speaking, Postgres always takes as much memory as it needs. And workmem is just, soft setting, like information, like we would like you to use this much memory, but Postgres says, okay, I will keep it in mind, but since I need more, I will use more. Here are again different results with different workmem settings of the same query. You can see how behavior changes. And when I set like very small workmem that 8 megabytes, it's actually used workmem 3.6 times in that query. Again, in absolute number, it's not that critical, 28 megabyte, what it is. But imagine 28 megabytes used by 1000 sessions at the same time. Yeah, we could have memory issues. So here is like parallelism for the same query, how it influences that query. And to summarize it, what to say? Postgres connections in general, when they are idle, are not so memory hungry as they seem to be in top command, because that top command was actually created for different use cases and is confused with those shared buffers which are attached to those connections. That workmem setting is also not a fixed per connection memory allocation. It is soft limit, may not be fully used, but it can be also exceeded. And we must understand that with parallelism, each parallel worker can exceed it too. So we must be very cautious with calculating max connections just from workmem and available memory. This is not enough. And this is all what I wanted to show you. If you have some questions, I'm not sure how to access.
Yes, there are two questions. I can read them.
Yes, please.
So the first one is how to calculate sum of network traffic from all PG processes.
Yeah, well, network traffic, this is like a different question, and I would like to dive to this also, because network traffic depends on how much data you actually transfer between that Postgres machine and your machine from which you run query and where you want to get results. So, as much as I would like to give you more information, I currently have only information about, this memory usage on that server, which sometimes could be like very critical. But I promise I will dive into this network usage because it's also interesting topic. But currently, I'm sorry, I cannot give you more info.
And the next question is from me. You showed the memory usage. The calculation for that is that like done manually. That you showed the numbers. You had a slide where you showed the numbers for memory usage.
You mean like these results from that S maps, something like
Uh,
this?
can you go back one slide? Yeah, that one. Sorry, that one. Yeah.
Yeah, this is actually output from top command. So if you
The
run top,
sorry, the next slide.
uh, like this one or
Yes.
this. Yeah, I created some Python code which summarizes those different paths from that SMAP file because it generally has several thousands memory regions. And to get some reasonable numbers, you must summarize it. But for our understanding, there is only one memory region, this def 0 deleted, which represents that shared buffers, and that anonymous and heap memory, they have more memory regions only when query is being processed. We have many Linux libraries attached to each connection, but first of all, these Linux libraries are shared between all connections. And second, even with like 200 libraries being attached to this connection, you can see that it's only something like 1 MB of memory in absolute numbers. So the biggest portion when connection is idle is used by Postgres binary. And there are some basic values of anonymous memory and heap. But if we run some queries here, we end up with shared buffers attached to that connection, which will now create those horrible numbers visible in top command, and it confuses users because what does it mean? Does that connection really use 8 GB of memory? Yeah, well, as I showed on those graphs, when query is processed, it uses some amount of memory which can be calculated from workmem based on our experience. So like 2 times, 3 times more than workmem, but it's not that critical. So generally speaking, Postgres connection is actually very good in memory usage. And those horrible numbers are all related to shared buffers, and we can forget them. But we would need tool which would say, yeah, this is resident set size with shared buffers, and another value, this is resident set size without shared buffers. And only with this tool, we would be able to understand that that connection uses quite a small amount of memory, but has some portion of shared buffers attached to it, which spoils that result.
Thanks a lot, Joseph. Thank you so much.
So
Yeah,
that's
let's have
all.
5
Thank
minutes
you.
break. Is a customer engineer and database specialist at Google Cloud. And his talk is titled Creating a Board Game Chatbot with Postgres, AI, and RAG. So let me know whenever you're ready to start.
I am. If I can share my screen, it's going to be fine. So I move forward?
Yes.
All right. Can you see my screen correctly?
Yes, it's good.
All right. All right. Welcome, everyone. I know it's been a busy day for you. It's only 5 p.m. Oh, I'm burning under the sun of France, but I guess it's pretty much everyone in Europe. So my name is Matt. I'm a customer engineer database specialist for Google Cloud. Basically, my mission is to make people successful with Postgres and other databases at Google. Outside work, I'm also deeply involved in the community. I'm vice president of Postgres France. I'm also co-organizing PGDF France. And just like Emma, I'm hosting a Postgres user group in Lille, which is in the north of France, a couple of times per year. So, quick disclaimer about this talk. First of all, this is not a commercial talk, even though I'm working for Google. This is an open source talk that I built for PGConf Europe in Hatton last year. And second point, I built it last year in October. So some information, some use cases I'm showcasing in the talk have evolved. I'm definitely gonna highlight those points during the talk, so don't worry. It's still very relevant, but sometimes I will pretend we are still in October 2024 to make sense. And as we are not so much in the call, feel free to raise your hand, ask questions, and we're gonna have a live discussion. I don't mind. All right, let's get started. So, a bit of context of why this talk. So, my wife is actually a board game shop owner. So, she sells board games to many people. And to do that, she has to learn rules of board games. So, she usually came back home with those games, and then I have to play with her because I'm a good husband. But sometimes, games can be very complex and difficult. So on a specific night where we were playing a very complex one, I had trouble remembering some specific points in the rules. And I was like, hey, let's ask a LLM. So for example, Gemini or ChatGPT or Claude. And the result I got was not the ones I expected. And I'm going to show you why this was different from what I expected. So in a very simple example here, I'm asking Gemini if he can tell me in the board game Monopoly how to get out of prison. And obviously he can do that. So he knows Monopoly, he gives me the right answer, formulates something that is correct, and we're good. But if I'm asking a very simple question about board game rules about another game called Castle Combo, a very recent game released in September last year. Actually, Gemini is unable to answer the question. Even though the question is very simple, it doesn't know what is Castle Combo. And the explanation of that is actually very simple. You obviously know Monopoly. It's a very old game. It has been released in 1935 compared to Castle Combo that was just released in September 2024. So if you look at the chronological order of release of games, you can see that, for example, Castle Combo has been released after what we call the cutoff date of Gemini 1.5. The cutoff date is very simply the knowledge on which the model has been trained on. So Gemini has been trained with data until late 2023. So for Gemini, Castle Combo hasn't been invented yet. So obviously it cannot answer questions about Castle Combo. So let's see how we can solve this actually, because we can. The first simple solution would be to use another LLM, an LLM that is more up to date. Another solution would be to fine-tune a model to train it on board games data. And lastly, the third solution would be to use what we call retrieval augmented generation. So the first one, using another LLM, is effectively very simple because you can just switch from Gemini to ChatGPT to Claude to whatever. But the problem with that is that sometimes the LLM won't just be up to date. LLM are not released like every day or every week. It's more like every trimester or semester or year. So having something up to date all the time is impossible. What about fine-tuning your own model on specific data? This is actually the best solution if you have unlimited money and unlimited time, because, you know, training a model takes time and it requires some GPUs and a lot of data. So it will cost you a lot to have something up to date. And let's say you train something on September and you have a new game released in October, the model has to be retrained once again. So the last solution might be retrieval augmented generation. But let's pause a minute here and let's see what it is exactly, RAG, what we call RAG. So this is the standard workflow when you are using a LLM to answer questions. So we have a user asking a question. This is usually mentioned as a prompt. The prompt is sent directly to Gemini, and Gemini, based on its data and the data that it has been trained on, will formulate an answer and go back to the user. And in our case, it's, I don't know. So let's introduce a new player to this game. And of course, this is going to be Postgres. So in this different workflow, we still have a user that has a question about board games. But this time, instead of sending the prompt directly to the LLM, we're going to generate what we call an embedding. An embedding is basically a vector representation of the question. It captured the meaning of it. Then we're going to compare this embedding to other embedding that are stored into Postgres. So we will have a database, a Postgres database, where we will have all the rules of all the games that were ever released, and we're going to calculate the embedding of the rules. So we're going to compare the embedding of the question and the embedding of the rules. Based on that, we're going to retrieve the rules of the game that we want. We're going to also retrieve the specific part in the rule book that we want to use. We're going to compute that into a new prompt, and then we're going to send it to Gemini. So the prompt will be a mix of the question, but also the data that we retrieve from Postgres. And this time, Gemini will be able to answer the question. So let's look at pros and cons of this solution. RAG, it's very flexible because, as you can see in the workflow, you can just plug a Postgres database with your own data and make it work. So in this presentation, I'm going to talk about board games, but you can think about your personal data, your business data, and things that LLM do not have access to. So it's a very good way to take advantage of LLM without having to train those LLM on your own data. Also, it is very interesting because you will always have real-time data. Your Postgres is a living database. So whenever you had a new game, whenever you had a new table, a new row into your database, this will be available for the RAG chain that we saw. The only cons here is that you need to have data to provide it to the LLM, but that's not really a con, because if we don't have data, then what's the point of everything? All right, so we're going to implement RAG. I'm going to describe how we can do this in Postgres, and later on, I'm going to show you how you can have it with performance and so on. So it's a multiple step workflow. I'm going to describe each of them just for the sake of comparison. Not everything is related to Postgres, but it will be interesting anyway. So it's a 4-step plan. First plan, we're going to collect the data. So I mentioned we're going to have a database with board game rules. Well, this is the step where we do it and where we store the data into Postgres. Then we're going to generate the embedding. Remember, this is the vector representation of the prompt and the rules. Next, we're going to do what we call similarity search. It's basically inside Postgres comparing a vector, how to do it. And lastly, very special part, we're going to talk about prompt engineering. That sounds like a joke. It's not. You will see why it's important. Okay, if you play board games, you probably know that website. It's called Board Game Geek, sorry, and it's probably the most up-to-date and exhaustive database of board games. So I went there, I extracted some PDF of the games I wanted to include in my database, and then I worked with this data to ingest it into Postgres. The problem with rules is that usually they are coming from PDF. Okay, so a PDF is not really something you can insert directly into a database. So what we have to do is to extract the data from it, and then we're gonna have more structured data that we can insert into Postgres. We can do that with some Python script. So for example, the PyPDF module is something that is working fine. So it can extract the data from a PDF. The problem with this solution is that it is not really intelligent. It will just crawl into the binary, the PDF, and extract the data it can see. So sometimes you will find out that PDF can be very complex files and that, well, the data is mixed up. So as you can see, the beginning of this page is stored at the end, and this thing is at the beginning for some reason. The other problem is that texts that are written into images cannot be extracted correctly. So instead of using this model, we're going to use AI once again. So for example, on Google Cloud, you have something called Document AI. Document AI is basically a model that has been trained to read PDF. So it can read PDF, it can recognize where the text is inside the page, and then it will correct it. So it's very different because it's not looking at the binary, it's looking at the PDF in its own user way. And as you can see, it's way more performant. Another thing that you could have do is use any LLM like Gemini, ChatGPT, or whatever, and feed the PDF to the LLM and do what we call structured output. Structured output is basically a way to tell the LLM that you want to get information on a document in a structured way. So for example, I want titles, text, and that's my model. And I'm telling the model that I want it to extract the text from it directly into those objects. So there are very various options these days to extract text from PDF, and very smart one. The next thing we're going to do, we're going to split those texts into chunks. Let me explain why. So in an ideal world, what we would have done is grab the PDF book of a symbol of a game, extract all the text from the rulebook, and then feed that into Postgres, and then feed the overall rulebook into Gemini during the RAG chain. The problem with this is that it's gonna generate a few problems. First of all, when you are calculating embedding, the vector representation of data, you cannot feed an unlimited amount of text. So those models, as of today, for example, this one, cannot do more than 2,000 tokens. A token is basically 4 characters. And in English, for example, 100 token is usually 60 to 80 English words. So if you take a basic board game called Wingspan, it's already 12,000 tokens. So it's completely impossible to ingest that into an embedding. So we have to split the data. The other reason is also because it's financially costly to generate embedding. So when you are feeding text to an LLM, so during the RAG chain, let's say we want to provide the LLM with the rulebook, the whole rulebook, you will be billed by the amount of token you are sending it to it. So it's way more efficient to only send a subset and more precise part of the rulebook than just sending everything. All right, so we're good. We can now insert those texts, those extracted into Postgres. you have to find a strategy on how to do it. It has to be related to the data. So in my example, if I want to have something precise, I want to make sure that every title and subsequent text is inserted together. So what I'm going to do is I'm going to insert each paragraph and it will represent a single row into my tables. Okay, we now have the data. Now we're going to calculate embeddings on top of this. So basically, this is the table that we have since we have collected the data and building chunks and so on. Now we want to do what we want to do is building a new column called embedding. But how do we calculate embedding? Well, I told you, you have to use a model that has been trained to generate this embedding. So those models have been trained to understand the meaning of the text and build something out of it called a vector. So that's exactly what we're going to do. We're going to feed all the rules to the model, and the model will get back with a vector. And as you remember, the vector is basically just an array of float. And in Postgres, thankfully, for a few years now, you can store those vectors into a new data type thanks to the extension called pgvector. So pgvector is a very simple extension. You can install it as any other extension. And once you do it, you will have access to, first of all, a new data type called vector. And you will also have access to new operators and new functions to manipulate those embeddings. So in the example on the screen, I'm adding a column called embedding with the vector data type, and then I'm specifying, a value, so 768. This value is basically the number of array your embedding is composed of. So if you have an embedding of 768 values, then you will need a data type of 768 values. It's quite a common numbers. You can have less, you can have more. And if you have more, well, the embedding will be more precise to extract the meaning of it. I see a question. What are some cons for doing things on embeddings with pgvector? What is exactly the question? Do you mean compared to a dedicated vector database?
Yes, exactly.
Cool. All right. So this was something I was going to talk a bit later, but to give you the main argument, first of all, your data already exists into Postgres. So if you would like to have a dedicated vector database, what you will have to do is to transfer the data from your Postgres to this new vector database. So you will have to build some kind of pipeline or ETL or whatever to feed the data to your new vector database. So it's two different engines, and you have to sync the data and monitor everything, and so on and so on. So that's the first problem. The second problem is that usually dedicated vector database can only do vector database. So if you want to have, combination of vector search and full text search and using Postgres for geolocalization and so on, you will be stuck because you will have to do the search on the vector database, go back with the result on Postgres, and do something more on Postgres. The good thing with Postgres, you can do all of that in a single database with everything that you know already. Indexing, backups, high availability, everything that you know just works with pgvector. Did I answer your question?
Yeah, thank you.
Cool. All right. So we have now the new embedding column, and now we want to feed it with the embedding. We could do that externally with a Python script once again. So we call an API, we call the database, we select all the rows, and we send each row to the model. We get back the vector, and then we update the table. If you are a Cloud SQL or AlloyDB user on Google Cloud, we have an extension called Google ML Integration, and you can do that directly inside the database. So it's a bit more convenient, and you don't have to build outside script. Okay, so now we've done that. We have a table with all the rules of the board games, and for each rule, we have an embedding. Cool. Now, what we're going to do is we're going to do similarity search. So what does that mean? That means we're going to calculate the embedding of the prompt, so the question of the user, and we're going to compare it with the embeddings of the rules. And thanks to that similarity search, we're going to be able to find the rules that will be that will allow me to answer the question. So looks like my clicker is gone. Okay, so how do you do that in Postgres? First of all, I want to explain what does that mean, comparing, embedding, and doing similarity search. So let's say we are working on embeddings with only 2 dimensions. So for example, this first page of the rulebook will have an embedding of 1 and 2. That's an example, of course. Let's say this other page from the rulebook has an embedding of 3 and 1. Then what we're going to do is going to calculate the embedding of the question. And probably this question will have an embedding of 2 and 0.5. So probably in this meeting, you are all able to say that the distance between those 2 points is shorter than the distance between those 2 points. Well, that is exactly what similarity search is. It's not as complex as it sounds. Of course, we are working with way more dimensions, but the principle stays the same. Now, how you do that in Postgres? So as I was mentioning, pgvector is coming with data types, but also operators. So for example, you can use this operator to compare embedding, the distance between 2 embedding. So in this example, I'm selecting all the rules, and then I'm ordering by the distance, and I'm limiting by the 5 best result, which means the closest distance between the embedding. You have many different operators that you can use. Each of them have its specificities. It always depends on the type of data you are comparing, the model you use to generate the embedding, and so on. The documentation inside pgvector is quite good. So if you want to have more information on those, you can just check it out. In this practical use case, we're going to use closing distance. It's probably the most flexible one and the most used for similarity search. And voila, we have now the table, the embedding. We know how to compare those embeddings with the embedding of the question. So we are all set. The last thing we need to do is work a little bit on the prompt. As you remember, I was mentioning that during RagChain, what you do is you take the prompt, the initial question from the user, and you augment it. Basically, what does that mean? That means we're going to take the question and we're going to feed it with also the data that we captured into Postgres. But we're going to do a bit more than that, because if you have used LLM, I'm sure you have, you probably know that sometimes they can be wrong, they can hallucinate, they can be convinced by nonsense, and also they can be biased by the data. But it's usually a problem of prompting, because the way we talk to LLM is sometimes too human-friendly. What we have to do is be very precise on how we want to talk to it. So here are a few best practices that you can use in your daily life, not only in RagChain. So the first guideline is to define the task clearly. So if you want to get a list, ask to have a list. If you want it to summarize something, mention that you want it summarized. You have to be very precise. It sounds a bit stupid, but the LLM is not in your head, in your mind. So you have to be very vocal about what you want to do. The other good best practice is to specify the desired output. If you want a specific order of sentences, you can specify it. If you want the LLM to output in HTML or JSON, just tell the LLM and it will follow you your guidelines. Other best practices are what we call few-shot learning. LLM are really good at following examples. So if you are providing example of what you want to get as an answer, it will copy your style. So it will copy the way you are talking, the way you showed it with the examples. So definitely show what you want to get. Show some examples. You can do one example, two examples, few examples. And lastly, again, this sounds like maybe a stupid advice, but it's not. It's very important. You can give your LLM a persona. Basically, what you are saying is that you are giving it a context. For example, if you want it to be a board game assistant that answer board game rules, tell it you are a board game assistant. Please only answer about board game rules. Do not answer about anything else. This will constrain the LLM and it will make sure that everything is in the right place. So in our use case, let's see an example. So the instruction, this is a pattern you can follow. The instruction is basically telling the context and everything we want to achieve. So in this specific use case, we are saying you are an assistant for question answering tasks specialized in board games. And at the end of the instruction, we are specifying that we wanted to provide the extract from the rulebook. It's nice. It's nice that it can understand the rule and come up with, a dedicated answer. But what I really want is the exact rule that was queried from Postgres. So I'm asking. Then I'm gonna provide a few examples. Here, I'm telling it, look, if you have a question like this, I want you answer like this and specifying here is the corresponding rule. Next, we're going to provide the context. This is the data we queried from Postgres, as simply as it is. And lastly, we're going to provide the question of the user. So if we combine all of that, a prompt that has been augmented in retrieval augmented generation will look like this: instructions, examples, user input, and the data, of course. Okay, so we are all set. All the steps are good now for our action. So let's see a short demo. I'm going to stop the share and share another one. Okay, so this is an assistant I actually built in something like 30 minutes last night because I wanted to have it up to date with new technologies, and I'm going to mention why. But anyway, it is behind the scene doing exactly what we saw in the presentation. So I'm going to ask a very simple question. How many keys do you start with in Castle Combo? When I hit the button, immediately the the agent will call Postgres. It will do the similarity search. So it will compare the embedding of my question, how many keys do you start with in Castle Combo, and compare it to all the rules in my database. And as you can see, he has been able to answer. So in Castle Combo, each player starts with 2 keys. Here is the corresponding rule. As you can see, he is following my pattern. Now let's ask a few more questions. For example, how to gain more? The funny thing here is that I'm not specifying the game. And the cool thing is that with agents, they have a history. So the LLM is now aware that we are talking about Castle Combo. So it's going to generate an embedding of my question, how to gain more, and the name of the game. And then we'll compare it once again with similarity search on Postgres, get back the rules, and formulate an answer. We can then switch context. So for example, we can ask a question about another game. How do you win in Pixies? So it's a very completely different game, but this time it will understand it's a different game and it will get back the rules and formulate an answer. All right. So everything is working as expected. Let's go back now to the presentation. Before we move forward with some performance topics and improvement that we can add, do you have any questions so far?
I posted one in the chat. Just wanted to know which LLMs you have tried, like have you used for this problem?
Yeah. So originally, when I started to work on this problem I had, this personal problem I had, I tested with all the LLM I could. So Gemini, ChatGPT, Anthropic, and so on. And all of those had the same problem because they were trained on specific data and my game was very recent, so they didn't know about it.
Mm-hmm.
So actually the LLM is not really the problem, it's the way we are using it. And that's why RAG is important.
Okay, thank you.
Okay, so we made it work. Now let's see how we can improve it. First of all, when we are talking about a RAG chain, usually there are two things you can improve. The first thing you can improve is the time for the chatbot to answer. And the second point is the accuracy of the answers. Because sometimes, well, depending on your chunking strategy or other things, or the prompt you've sent, the prompt that you built, probably sometimes it could not work. It could not build the sufficiently enough accurate answer. So if you want to improve the time needed to answer the chat of the chatbot, you can play on many different things. For example, the capacity of the LLM. So it's basically a problem you cannot solve on your own because it all depends on the platform you are using. But you can also play with Postgres. As we saw, a huge part of RagChain is doing similarity search. So if Postgres is slow, if the similarity search is slow, then the overall application will be slow. So we're going to see how we can improve that. We are Postgres users or DBA or whatever. So we do know that one of the first things we can do to improve queries is indexation. In vector search, you have two ways to use similarity search. So you can do what we call TNN, or we can do what we call ANN. TNN is basically finding the best possible answer. And the only way to do that is to go through all the rows in my table. That's the only way. I'm going to compare the embedding and find the best shot in those tables. The other way is to do ANN. ANN is called approximate nearest neighbor. This time, we are not looking for the best result, but for the best acceptable result for the performance I want to achieve. And this is where we're going to work with indexing. So in PG Vector, you have two kinds of index that you can use. New ones. The first one is IVF flat, and the second one is HNSW. Providers such as Google have come up with other methods. For example, at Google, we have Scan. Scan is basically an implementation of what we are doing on Google Search, Google Photo, Google Ads, and so on, directly into Postgres. So it's another method that you can access when you are using our technology. How does that work? IVF flat first. So when you are building an index of IVF flat, basically what you are building is a grid. So you are placing all the embedding in the index into a small group. And all those groups will have a center. Okay. Then when you want to compare the embedding with this index, you will put this embedding on the grid. And thanks to it, you will use all the grid that are the closest to your embedding. So you will be able to get all the result in those grids and provide the probably best answers. But if obviously the best answer were in another grid that was not chosen by the IVF flat, you will not have the best answer, but still you will have a good answer. The other indexation method is HNSW. HNSW is probably the most popular indexation method. It's available on PG Vector, but not only. So other vector databases are also using this algorithm. The idea is to work by layers. So we're going to take the overall embedding of the index and we're going to split them into layers. So on the first layer, I'm going to take the embedding that are the farthest from each other. Then if I want to find the closest point to this, I will step down to the layer before. Yes, I will finish in 5 minutes, don't worry. So if I want to find the closest point of this one, I'm going to have to go through the next layer. So I'm going to find the closest to the entry point and then go down on the point I found that is the closest one. And I'm going to repeat this process layer by layer. And when I've reached the last layer, I will be able to find the closest point in my index to answer. You can parameterize the number of layers you want. The more layers you have, the more precise your search is. The less layer you have, the more performant it is. So it's a trade-off choice. Another way to improve vector search is by doing vector quantization. It's basically a technique to reduce the size and complexity of the vectors. As you saw, vectors are just array of floats. So if you want to rationalize those, you can by doing some quantization. Quantization is a technique to, for example, remove some numbers of those float. So instead of using a float 32, you can go for a float 16. The idea is that the more numbers you have, the more precise you are, but it's also bigger to store and to index. So if you want to be a little bit less precise but more performant, you can remove some numbers. You can be even more aggressive. So for example, you can transform all the float into 0 and 1. This will be very cheap to store, but of course, you will lose precision. So this is an example of how you do it and the things I mentioned. And lastly, the last technique I want to present is what we call hybrid search. And this is one of good thing of Postgres. Hybrid search is the capacity of doing semantic search, so what we just saw, and full text search. If you combine all of those, this will be what we call hybrid search. The idea is to do two queries. One query that is doing full text search, so using TS query and TS vector, things that you probably already know. Do the same thing for the same query for the same question, but with semantic search, and then combine the result. So we're going to use an algorithm called RRF, a reciprocal ranking fusion. We're going to combine the result of the two queries and come up with the best result from both of the worlds. This technique is really good because you can mix the usage and you can improve the performance and the accuracy of your queries. You can do both in a single technique. So it's really nice. Key points, a few takeaways. So Emma, you already mentioned this in the question, but vector search on Postgres is really good because you can mix usage. You can do vector search, but you can also do full text search. You can do Postgres. You can do whatever you are already doing with Postgres, and now you can combine it with vector search. Prompt engineering is not a joke. It's very important if you want to constrain the LLM to do whatever you want. And that's pretty much it. The tools I use to build the agent you saw during the demo is called ADK. It's an open source framework that you can build to create agent and do exactly what I saw in what I showed you in 50 lines of code. And the other tool is MCP Toolbox. It's basically a bridge between the agent and the database. Thank you. And if you have questions and if we have time, I'm still here.
I think no more questions in the chat. Thank you so much, Matt, for the presentation and for your time.
Sure.
Yeah, let's have a 5 minutes break and let's do our last session. Luigi. He's the founder and CEO of DBTune, and his talk is titled Auto-Tuning Postgres, a deep dive into server parameter tuning with machine learning. Yeah, let me know whenever you're ready to start.
Hi, Emma. Thank you very much for your kind introduction. I will share my screen real quick and we can get started. Can you see my screen?
Yes. Yes, it's good.
Good. All right, so let's get started. Thank you very much to Emma and the organizers of this PG Armenia Virtual Summit. This is a very exciting event. I'm very excited to be here. I'm Luigi Nardi. I'm the founder and CEO of DBTune, and today we'll be talking about auto-tuning Postgres, a deep dive into server parameter tuning with machine learning. This is a topic I've been working on for about, let's say, 5 or 6 years. And at DBTune, that's the topic we focus on. This talk will not be about DBTune specifically, but about the lessons learned during this journey that led to building a production-grade server parameter tuning that uses machine learning in the process, right? So that's let's get started. I just wanted to introduce myself very briefly before starting. I'm a computer engineering major, and I have a mixed background in academia and research. So I have a PhD in computer science and applied mathematics from Paris, and in Paris, and from Paris moved to London, worked at Imperial College for a few years as a postdoctoral researcher, and then joined Stanford University as a research staff. And moved back to Europe as an assistant professor in AI and machine learning at Lund University in Sweden, and founded DBTune in 2021, even if the project was already started a couple of years earlier. Very briefly about DBTune before I start on the topic. DBTune is an AI-powered Postgres server parameter tuning service spun out of research at Stanford University. And this is really this idea of autonomously optimizing the configuration of the database or the server through machine learning. And the idea of observing, adapting, and iterating until convergence and delivering the optimal server configuration for any individual workload, use case, and machine. Okay, so we will talk more about this topic, but I wanted to briefly mention what DBTune does. And I'm very proud that last year, DBTune was one of the top 20 sponsors for Postgres events in 2024. Hopefully, we will repeat that in 2025. We've been giving trainings at Postgres events since January 2023. This is an example in the PG Developer Day in Prague. And we've been also part of the organization of a similar Postgres user group as the one that is hosting this event today in Armenia. This Postgres user group is the one that we are organizing in Malmö in Sweden. And these are the 4 organizers. We kickstarted this user group about a year ago, almost a year ago now, and this has been a lot of fun. Good. So let's introduce first Postgres server parameter performance tuning. I will give a short introduction of that. I will give some quantitative illustrative examples, and then I will talk about how is this problem solved today, and then deep dive into the machine learning tuning automation. And this is really the idea of using AI agents for Postgres tuning. We'll talk more about that. And I will spend a few minutes as well talking about the safety of this. So how can we use machine learning and AI in production systems in a safe manner? Because of course, performance is very important, but the safety aspect is even more important than the performance that you can squeeze from a server machine. Okay, I will give some examples, some quantitative examples of auto-tuning at DBTune, and then we'll talk about some conclusions. And I like this topic of talking about the user psychology when you deploy an AI agent in production system. So I will talk a little bit about that as well. It's a fun topic. Right, so what is database tuning? Okay, so this is really the idea of keeping the database fit and responsive, right? So the idea here is that databases are very dynamic objects. They change, they grow and slow down over time. And not all workloads and machines are the same. So if you go on AWS or Azure and any other cloud provider, or you look at all sorts of data centers, there are a number of different machines in terms of like hundreds of different configurations of machines with different types of RAM, different types of disks, different types of CPUs. And so this is a very heterogeneous environment. Some of them are NUMA and one not. And the workloads as well are very diverse, and there's a spectrum of different workloads from read heavy, write heavy, and so on. And the combination of all of this makes the environment quite challenging. And the idea of tuning is really this idea of adapting a database to its current use case, load, and machine. Okay, so this is really trying to do something that is specific to you and your use case, and it's not generic to any given machine or use case, right? The problem is considered a bit of a dark art, but it's the integral part of any database administrator or developers as well. These days, developers manage databases as well. And it's a bit of a dark art because this is a really challenging and complex process where you try to iterate through a number of changes of your server manually to get to a good solution. So it's very challenging. I will talk a little bit more about that in a couple of slides. The idea here is that tuning includes several parts. There is the query tuning, which is basically the tuning of the SQL statements. Changing the SQL statements can deliver better performance, of course. The server parameter tuning, which is the topic of this talk. So today we'll really focus on the Postgres server parameter tuning part. But you can also tune indices, for example, and you can even tune operating system parameters, right? Which is a topic that is not really explored as much in the community, but it's very interesting as well. So when we talk about tuning, we usually talk about all these different things. And all of them are equally important, right? But for this talk, we will really focus on this topic, which I think has been pretty much neglected for a long time, and we'll talk about the potential of server parameter tuning for your production system and how good of an impact it can have if you handle this type of tuning. But first of all, why does it matter? So from a technical perspective, when we look at the impact on system performance, we're talking mainly about the performance improvement on throughput, and which is usually measured in transactions per second, and latency, which is often measured as average query runtime, for example, or P99, for example. So from a technical perspective, those are things that engineers usually care about and want to achieve high throughput and low latency. It's very important things. But there is also high scalability, which is a very important topic. But the stability of the database as well is an important part of this. And of course, meeting the SLAs. If we focus a little more on the business side of things, this is also very important. And there is a direct connection between the technical perspective and the business perspective. When we tune databases and we make them well-performing and healthy, we achieve decreased infrastructure spend. And I will touch upon this topic in a few slides a little more in detail. But the idea is that by running efficiently your database, you can rightly size the instance, and you don't need to over provision your servers because you can run for your SLAs. You can run at that level of SLA with a specific server without having to over provision. Right? There is of course higher end user satisfaction as well. You reduce the downtimes, you increase productivity, and you can also save energy. And this is a big topic. I will not talk very much about this in this presentation, but there is a blog post that I wrote wrote a little while ago and was picked up by Data Center Dynamics and published. So if you're curious, please feel free to ask in the chat, and I will post the link to the post, to the blog post on that topic. It's a very interesting topic, in my opinion. Right, so let's go a little more into the details of what Postgres server parameter tuning is. And I really like this picture because while this is an audio console and it's different from, of course, server parameter tuning, but the problem really looks a little bit like this, right? So you have all these different knobs, and what you're trying to do is to find the right combination of the knobs in a way that you achieve high performance, right? And this is a pretty complex combinatorial optimization problem that requires a lot of expertise in Postgres as well. And the examples here that if you've been working on Postgres for a little while, that you probably have seen in your work is parameters like work mem, shared buffers, max vault size, etc. And I will introduce a couple of parameters here just to go a little more in detail into a couple of those. So here, for example, max parallel workers per gather is a parallelism parameter in Postgres. And what it does is to define the maximum number of workers, of parallel workers, that can be used inside one query to perform the work in parallel. So if you have a complex query and you want to perform the work in parallel in that one query, then this is the parameter that you will tune to achieve that parallelism. And then, of course, there is the gather merge node, which puts all the results together of the different workers and kind of merges the results in one result. So this is one of the parameters. And this is a parameter that really affects one part of your machine, which is the CPU side of things. A second example is random page cost. And random page cost is a parameter that affects the disk and more specifically affects the way the planner estimates the cost of a non-sequential scan of these pages. So you're accessing a number of disk pages and you're accessing them in a non-sequential manner. And this parameter, random page cost, defines the cost that the planner will use to basically define the plan for executing the queries, right? So this is a parameter that it's related to the disk. And back in time, when we had the spinning disks, this random page cost value will be very, very high because the cost of accessing non-sequential fetch these pages was very high. And with SSD, it's usually smaller. But this is a complex parameter that affects the way the planner perceives the disk, right? And the I/O in general. So the idea here with server parameter tuning, and if you go back to perhaps your 101 computer science classes, there is the von Neumann machine, right? Von Neumann machine has these three components, which is, the I/O and specifically, let's say the disk, right? And the memory side, and then there's the CPU side. And of course, the data flows from the disk through the RAM and memory through the caches, and then gets into the registers of the CPU where the data is processed. And the idea of server parameter tuning is really this idea of tuning and configuring this von Neumann machine so that the data can flow from the disk to the registers of the CPU and can be processed very quickly. So this is a von Neumann machine optimization, if you'd like to see it that way, okay? Well, the bad news, though, is that these parameters, which affect these three parts of the von Neumann machine, the disk, the memory, and the CPU, these parameters highly depend on the application. So if Emma comes with an application and tunes the parameters, server parameters, well, the solution to this problem will be one specific solution. And if Harry comes to me and with another application, the solution to that problem, then would be a different solution, right? So you get two different solutions based on the applications. And I would like to specifically talk about this a little more, because I think this is a key aspect of this server parameter tuning and the dependence of these solutions on the application itself. So I will go a little more in detail on that with some illustrative, quantitative examples. So here we're seeing an application called Opinions. This is a benchmark that you can download from the internet. So it's not specific to us. It's just a benchmark that we downloaded from the internet called Opinions or opinions.com. And the idea here is that I'm showing the two parameters, max parallel workers per gather, which is the parameter I introduced in the previous slide, and random page cost. This is also another parameter that I introduced in the previous slide. I'm showing on the vertical axis the performance, which is measured in query runtime in milliseconds. So here, lower the better. So meaning that lower number here, it's a better outcome for the performance tuning. Here specifically, I'm not doing any tuning really. I'm just taking all the values on this axis and all the values on this axis. I'm taking the Cartesian product of the values between the two axes and basically running the benchmark with this combination of the two parameters and showing all the possible configurations in this optimization space. This is what is called exhaustive search. So we're basically doing all the possible combinations in this Cartesian product, okay? What we can see here in dark blue is the good region. So the region that leads to lower average query runtime, which is below 1 millisecond. And in yellow, we can see the region which is not doing really well. And this is above 8 milliseconds, right? So if you look at the yellow versus the blue, the dark blue, you see that there is roughly an order of magnitude difference in performance from doing it well, which is this little corner here, and not doing it really well, which is all this yellow area over here. So it's quite interesting to see that there is this order of magnitude difference in performance from good and bad. The same thing can be observed in a second benchmark. Again, this is a benchmark that you can really download from the internet. It's called TPCH, and it's a more analytical workload. And so you can see that this is analytical by the fact that the queries are much more expensive to run. So in average here, they're much slower than these ones. And here what we can see is on the axis is same two parameters here, max parallel workers per gather and random page count, the same as here. But what you can see here, so first of all, you can see that the performance variation between doing it well, which is this dark blue here, and the yellow, it's again one order of magnitude difference in performance. So the same variability in performance can happen in opinions and in TPCH. So the performance on the table between doing it well and doing it badly is this order of magnitude performance improvement. But the second thing that we learn is that the dark blue and the yellow, they are in different positions in this graph. Okay, so here the dark blue is here in this corner over here, and the dark blue, which is the good part, it's in this corner here, bottom right. This basically means that TPCH likes having highly parallel workers, while the overhead of having parallel workers is actually not very good for opinions. And that would be quite challenging to know ahead of time. You should really study the application and try to really understand what's going on to set up these parameters properly. But this is what I was saying before with respect to Emma coming with opinions.com, for example. The solution would be this little corner over here. But if Harry comes with his own application, perhaps TPCH, then the solution is actually this corner over here. So the solutions are different, okay? Depending on the application. So we have learned mainly two things from these two charts, right? So the first thing is that there is an order of magnitude performance improvement from doing it well and doing it wrong. And the second thing is that the solution, the best solution really depends on the application. Here in opinions is this corner over here, while TPCH is this corner over here. But there is a third thing that we can learn from these plots, which is a little more subtle. And this is related to the way database administrators really perform this tuning usually. The tuning is usually done by tuning one parameter first, then fixing that parameter and moving to the second parameter, and then working on the second parameter until we think we are done, and then moving to the third parameter, and then basically going through a number of parameters in a sequential manner, right? And we rarely go back and change what was decided in previous steps. So the sequential scan of these parameters is done in a kind of a one-way fashion. The issue, though, is that if we optimize parameters in a sequential manner like that, what we're doing here is basically going through this access in a kind of a parallel manner. So we go, for example, like this and like this. This will be an example. And this is what in optimization, in mathematical optimization, is called coordinate descent. But usually coordinate descent, we iterate and we go back and sequentially scan the different axes, but we go back and scan them again. While instead in the real world of database parameter tuning, doesn't happen usually like that, right? So this basically means that we may miss the opportunity of finding this little corner over here or this little corner over here if we can just move on parallel axes like this, right? In practice, what we want is to be able to move diagonally and try to find this corner by moving diagonally, right? So to sum up, we have learned three things from these two plots. So the first thing is that we have this order of magnitude performance on the table from doing it well and doing it poorly. The second point is that the solution of this problem really depends on the application. Here is this corner over here, and here is this other corner over here. And the third thing is that the current way of doing tuning manually, it's really not ideal because it does this sequential scan of the parameters, while we really benefit from having a joint optimization of the parameters, which is something that we are not very good at in general at doing, right? So that's why I think that machine learning and machines can just help us algorithmically can help us to solve this problem more effectively. All right, so if we look at the number of parameters over the years for Postgres, things are getting a little complex over time. So if you look, for example, from 2005 to 2025, there has been an increase in terms of a linear increase in terms of parameters. In the last perhaps 18 years or so, we've seen a 2.5x improvement in increase in the number of parameters. So we went from about 100 to about 300, actually 370 in the last, Postgres 17 release. And this is a problem because increasing this is a combinatorial optimization problem that we are tackling, and it's a very complex problem. The good news, I would say, is that not all these parameters are important for performance parameter tuning. In practice, there are parameters that just the names of the logs, for example, and this doesn't really matter for performance tuning. But I would say to keep it large, there is at least between 10 and 25 parameters that are really, really important for performance tuning. So let's just maybe focus on 12 parameters, right? So what does that look like? So 12 parameters already gives about 1 trillion possible configurations of the server. So this is a very, very large number, and it would be very, very challenging to tune these 12 parameters in a joint fashion, right? The important thing, though, is that if you move from 12 parameters to 11 parameters, you can see that there is a big step from perhaps 100 million parameters, 100 million possible configurations of the server to 1 trillion possible configurations. There is a big step, which basically means that when we add one parameter, the problem becomes exponentially more complex. In other words, it's not just a little more complex, it's much more complex, right? And so we need to be really careful by adding more parameters in Postgres, because the complexity really can become really, really challenging. And so I'm showing here that even with 12 parameters, the problem is already daunting. So how is parameter tuning tackled today by database administrators and developers? So the state-of-the-art solution today is manual tuning. Manual tuning is a process that can be quite slow. It may take many hours if you really are an expert, but it may actually take even days, even weeks sometimes to really solve this problem in a production system, in a system that is very large and complex. It needs a lot of expertise. I've talked with many Postgres engineers that have been, working on Postgres for a couple of years, and they still don't feel comfortable in changing these parameters by themselves. So it's usually more senior Postgres engineers and database administrators that tackle this problem. This is also slightly ineffective because tuning needs to happen regularly. You cannot just tune once and forget. And I will talk a little more about that in the next slide. And there are all these seasonal workload effects, right? So there is a Thanksgiving workload, there is a Christmas workload, and so on. And those things need to be tuned specifically to that seasonal fluctuation, right? And when I think about manual tuning, I think about my manual tuning guru, who is Magnus Agander, one of our colleagues at dbTune, who has been working with us for about 5 years on this problem. And when I really have some troubles in understanding how I should do manual tuning, I really go to see Magnus, and he helps me understand all the nitty-gritty details on how to do this really, really well. So there are many people probably also in the audience that have this type of expertise. Magnus is, of course, a close colleague and a role model for me for this type of problems. But there are quite a few experts in this manual tuning area, and I'm assuming that you guys are one of them, or may have a person that you refer to for this type of problems when you have this type of problems, right? There's a second category, which is very interesting as well, which is based on heuristics. And this is the idea that when you, for example, use an RDS instance, RDS instance will come with some heuristic-based parameters of the server, which you will be using out of the box. But there are also other services out there, for example, pgtune and the Postgres configurator by Cybertech, which are fairly simple tools that allow to tune the server parameters. pgtune, for example, is also open source, so you can look at the way it's implemented. But the issue with these tools is that it's a bit of a one-size-fits-all solution because it uses generic rules on how to do this. And I will have a slide on discussing how they look like a little more in detail in a couple of slides, because I think these are solutions that are very well adopted in the industry. And I think if you didn't use those, I think you should certainly adopt them because they're very, very useful. The main issue with pgtune and Postgres configurator is that they're workload agnostic. They are not bespoke to your workload. And if you tune again in a week, they will just give you the same solution. So they don't adapt and adjust with respect to your workload, right? If you change machine, they will make some adjustments to the solution. Otherwise, they will just give you the same result over and over again. And they don't respond with seasonal workloads. They're just the same, always the same. So this leads us to the third category, which is this ideal category, which is the AI-driven approach. And this is really the approach that is about learning from the real-time metrics that come from the server. And it's an agent that is plugged in your, and I can watch and look at, and monitor and observe your Postgres instance and learn patterns by observation and automatically tune the Postgres server. Okay, so this is a solution that adapts to changing workloads as well. So this is kind of the idea, the holy grail of server parameter tuning. And this is, of course, what we do at dbTune. As far as I know, we are the only company that does this in Postgres today. But this is an interesting area that we've been focusing on for about 5 years. And I will share some of the learnings that we had in focusing on this specifically at dbTune. But before we talk about heuristics a little more in details and the AI approach a little more in details, I just wanted to talk about this question of a question about how often do we tune, right? And the reality here is that there are some frequent triggers for tuning. And this is, for example, when your workload changes. Here we are talking about, for example, if your queries change. Let's suppose that you are developing the application, you're in the process of adding a new feature in your application, and that adds additional queries, for example, and this leads to your workload that has changed. And so if the workload changes, you have to retune, right? And this may happen quite often if you are developing your application and if you're adding additional queries to your workload, right? Adding or changing them. Another reason for tuning is if your database is growing. Let's suppose that your database is growing by 1 terabyte or 2 terabytes every couple of months or every 6 months. We have seen this type of scenarios quite regularly. It's not uncommon to have 1 or 2 more terabytes every 6 months, for example. And these are all scenarios that really lead to the table statistics that change. In practice, when table statistics change, they often change in a step function way. So you have 100 rows in your table, and then you add 1 more row, and the planner will pick up on this statistic change and completely change the planning, right? The plan for executing these queries. And that basically means that you may go from a tuned system to an untuned system in a matter of like literally adding 1 row because the table statistics have changed. So you need to keep an eye on the performance of the system, and when the performance and it's convenient to kind of tune the system when this happens. There is also this question of scaling your cloud instances up and down. And of course, if you're changing the hardware by scaling up or down, that's certainly another reason for tuning. And this is something that maybe didn't happen as much in 2010 or something like that. But in 2025, in the cloud era, this really happens quite regularly, like people changing their database instances, the underlying hardware by upgrading the instance or downgrading the instance. That happens quite regularly these days. So those are all reasons that are quite frequent that happen now and then, and that will trigger an event for tuning the service again, tuning your instance again, right? However, there are also infrequent reasons for tuning. And this is, for example, if you're migrating from on-prem to the cloud, or vice versa, which also happens sometimes, even if it's not as common. If you're migrating from a database management system to another database management system, here, for example, from Oracle to Postgres, this is certainly a reason for tuning as well. Or if you're upgrading your version of Postgres, so there is a new major release of Postgres every year. So if you're a good Postgres user, you probably upgrade every year. This doesn't happen as much like that, unfortunately, but this is generally speaking a reason for infrequent tuning, right? So all these reasons, frequent and infrequent, are all triggers for tuning. However, in practice, what happens is that the tuning is very often treated more in a reactive manner when something really goes wrong, where your servers really, the performance server really goes wrong, and instead of a proactive approach, right? And this is a commonplace, and this is especially a commonplace because very often you need to engage with expensive external consultants and experts, to do this, and it's very difficult to have people internally in the company that know really well how to do this. You may have a database fleet which is counted in the tens or hundreds of database instances, and you may have a small database administrator team, which is maybe 2 or 3 individuals, and it becomes really, really challenging to do tuning more regularly than once in a while. Okay, and the modus operandi, I think it's the fact that the workloads are not treated differently very often. They're just basically given the same configuration across the fleet. And we tend to throw more hardware and compute to any issues that we have, which means that, the $3 there means that this is very expensive and you're basically over provisioning. So there is a overall trend on over provisioning, and there are many studies on this. It's very common, and I'm betting that in your company as well, you will probably be over provisioning, meaning that you will be using a much bigger instance than the one that you actually need to achieve your SLAs. Okay. So this is something that it's really related to the fact that all the tuning happens manually. But if we move into a more automated approach to tuning, then we can move really from this reactive to proactive approach, where tuning is then seen not anymore as an activity that you do once in a while, but you can think about that as a maintenance activity. Instead of getting your server performance to slowly go down until really breaking your system, you can think about the fact that it goes down and then you bring it up again regularly, every week maybe, because it's just a maintenance activity that you can run automatically to bring it back. In the same way you do backups regularly and you do other things regularly, your other maintenance activities regularly, right? So this is kind of a mindset shift from manual tuning to automated tuning, which can lead to seeing tuning as a maintenance activity instead of a once in a while activity that needs to be done when the performance really gets really bad. Okay. Okay, look, let's talk about a little more about the solutions that I described before. So I talk about heuristics, and pgtune is an open source tool. It's very well adopted out there, and this is how it looks like, right? So you have a few parameters, and you define this memory size, for example, here, the number of CPUs, and a few other things. And this literally, by pushing the button generate, it just generates the configuration that you then copy paste into your pgconf, and you're done. So it's a 5-minute activity. It's great, and I really recommend that you use this if you didn't use it before, because by using this you can already achieve a much higher performance than the one that you have right now. Okay. So absolutely check it out if you didn't use it up to now. Okay. The issue with this that you can see is that the parameters that you define here are related to your machine type, but this is not very much about your application. And this is not really watching what's going on in real time from your application. It's really just getting some parameters that depend on the machine. And these parameters won't change if the workload changes. You would like to tune the system in a different way, but pgtune won't help you with that. So it's not workload aware, it's workload agnostic, right? And similarly, the CyberTech Postgres configurator, you can see that it's very similar in terms of the interface is slightly different, but it's just asking for the similar type of parameters, right? And you can see that does roughly the same thing. So now we will switch gears and try to talk a little bit about how would you do this with AI and machine learning. And this is kind of the desiderata. Desiderata means, what do we want from this system, really? So if we had to specify, give the specs of like what would be the ideal scenario for server parameter tuning, well, this will be based on a machine learning approach. And it's based on machine learning because here we want an agent that learns to solve workload-specific optimization challenges. So there is a learning aspect that comes really from this machine learning technology, which is important. And the dynamic adaptation is really related to the fact that you want to give different answers to different workloads, right? So different applications will need different answers. And this is really the idea of auto-tuning with respect to a specific workload, with respect to a specific size and complexity of the problem. It needs to be really easy to use because we're not all experts in machine learning and AI. And we also would like to provide a solution for maybe developers that are not huge Postgres tuning experts, for example. So these two aspects are not being machine learning experts, but also not being gurus in Postgres tuning. And so being able to do this without being a really good manual tuner, right? And then the scalable part as well, which is the idea that you like to tune a full hour fleet, right? So you don't want to just tune an instance. If you have 100 instances running, well, you would like to deploy this and just tune them all on a push button, right? So that would be really the ideal scenario. So this is the high-level desiderata for Postgres auto-tuning, and this is the vision behind this type of work. And I think it's very important to spend a second on what are the user value propositions here, because the most obvious one is this one. So your service becomes radically faster, right? So that's great. You were running at 10 milliseconds, your average time. Now you're running at 2 milliseconds, for example. So that type of improvement in performance, right? or from 1 second to 50 milliseconds. So this is the type of performance where you can see. And but at the same time, if you can do this automatically, this will free up your database administrator time. And of course, database administrators today are very challenged by very large operations. They're running around doing all sorts of operations, and taking this one task and just providing a tool and being able to automate this, it's really, really convenient, because database administrators can focus on other equally important tasks, right? And then there is the reduction of cloud and infrastructure costs. And I would like to spend a couple of slides on this in a minute. Just I want to quantify what that means. So let's keep this in mind, and I will talk a little bit more about that in a minute. And then there is, of course, the reduction in energy consumption that, as I said before, I will not really touch upon very much in this presentation. But keep in mind that that's also a very important aspect that you can achieve with this automation in tuning. All right, let's look at what this would look like from a high-level architectural perspective. So here we have your Postgres instance over here. Here we are looking at a self-hosted Postgres use case. The Postgres self-hosted instance is over here. We install an open source agent. The open source agent does two things. It monitors and it actuates. The monitor is a little piece of code that gets the monitoring metrics from PG statements and similar things, but also CPU usage and memory usage and things like that, disk usage and things like that, and reports this information, these metrics, to the machine learning optimizer. And the actuator, it just does one thing, really. It just changes the pgconf in the so in the configuration file for Postgres, right, for the server parameters, right? This is all it does. And on this side, we have the optimizer instance. So this is a terminology that we created at DBTune, Optimizer as a Service, or OAS. And the idea here is that it's a SaaS, it's a software as a service, but delivers an optimization service. And we create a term for this just because we believe that there will be more and more optimizers as a service in the future. So it made sense for the industry to just have a name for this. So this is our OAS, or in general, the OAS for server tuning here. And the machine learning optimizer runs here. What it does is that the monitor reports these metrics over here. It suggests basically recommending a configuration to the actuator. The actuator actuates the configuration, and then the Postgres configuration has changed. This is run for a number of minutes, and then the monitor will get all this new information, which is then reported again back to the optimizer. The optimizer builds a model, and the model is probabilistic in nature, which means that it will get better and better understanding over time and refine the understanding of what's going on the left side over time. And so these iterations go on and on for a little while until then eventually the models here, they get a very good understanding of the Postgres instance performance landscape, and it will recommend some very good configurations of the system, right? So this is the prior learnings here. It's what we call prior learnings is this idea that we can warm start this optimization process by getting all the knowledge from our manual database administrator experts that have done this manually for a long time. And so we have that kind of domain expertise, but it's also the expertise of running a lot of experiments in the past and adding this expertise in what we call the prior learnings. The prior learnings help to solve this very complex combinatorial optimization problem in just a few hours, right? Which is, I think, a technological breakthrough by itself. So if we can use this and just push a button with a few hours and get results, a few hours to solve a complex combinatorial optimization problem, it's a really interesting value proposition for this type of problems. Okay. So this is how it looks like for self-managed Postgres. If we move now into the database as a service, and here I'm talking, for example, about RDS. or Postgres, RDS Postgres or Aurora Postgres, for example. Here you see that the scheme is very similar, but here the agent needs to talk directly with a library that it's, for example, this is an example, the Boto3 library, for example, where it just basically allows through this API access to change the server parameters through the actuator, and the monitor will basically access Amazon CloudWatch, for example, and the rest will just stay the same, right? So this is a small change that needs to be made at the agent level as an adapter to basically support the Amazon RDS in this case, and Aurora works in a very similar way. Very similarly, and I will not spend very much on this, much time on this, but Azure Flexible Server will work very similarly, or Google Cloud SQL or AlloyDB. I think it's just the same, similar, and we went through the process of integrating with a few of these database services. So this is really how it looks like. So a small change in the agent, and the rest of the system is basically untouched. One important thing that it's important to mention is, and I didn't mention this very much in the desiderata of this machine learning driven optimization, but very often very large enterprise customers ask us to run this not as an OAS, an optimizer as a service, but they want to run this in a small container in their virtual private network, completely disconnected from the internet. And this is especially true in 2025, where all the geopolitical turmoil and the wars and all these cyber security issues that are very, very top of mind in IT departments of these days, right? And so this is something that it's very important, not just from a business perspective, but from a technological standpoint, because this basically means that you need to be able to run this online machine learning model. So this model is being trained on the fly in an online manner, and you need to be able to basically run this in an image that you need to be able to ship to a customer or a user that would probably not have massive GPUs or a GPU cluster to train this, and the training needs to also happen in a decently short amount of time, because otherwise you will spend a ton of time training this thing and you will never get your tuning done, right? So I just want to put it there because it's an important aspect that it's really related to the technology. So how do you design this machine learning optimizer in a way that it can really fit this desiderata of being run in a self-hosted manner as well? So the example of parameters that the tunes today is this list. This is the set that we tuned today. The list has been extended over the years, and keep an eye on this link if you want to see the future parameters when we add them. The list is being extended every other every now and then, every release. There is sometimes new parameters that come up, but there are mainly two categories of parameters. There are the parameters that don't require restart. They can just use a database reload. So these parameters here don't require any downtime of the system. And then there are these two parameters here, shared buffers and max workload processes, which are two parameters that require a restart of the database instance. And this can be really a problem for applications that have not really been designed for having these short downtimes, right? So if you want to go to this process of changing the configuration multiple times before converging into a solution, you need to change these parameters a few times. And if you need to restart the database every time, you have this short downtimes, maybe 20-second downtime every now and then, right? Which is really not suitable. And so the news is that shared buffers is currently there's a patch go check the hackers list. There is a patch that is making shared buffers dynamically adjustable, which is really, really great. So we should expect, perhaps not in Postgres 18 that is coming up soon, but maybe in Postgres 19, we should expect perhaps the shared buffers will become a dynamic parameter, which will mitigate this issue of restarts. In practice, there is a alternative approach where you can, for example, restart your server only once and define this heuristics for the shared buffers and max working processes. And we observed that if you use this restart once approach and you set up them at these values, well, you actually get, it's the 80-20 rule. You really get a very good baseline. Of course, you don't get all the performance you can squeeze from your server, but this is a very good way to set up the baseline. And then you basically can just tune the reloads. And I will talk a little bit about this in terms of like performance, the performance results that you get by having this, start once approach. All right. I just wanted to briefly mention that the aspect that it's very often discussed as well when we talk about performance tuning is really the safety side of things, right? So it doesn't really matter if you can make the server as fast as you can, but then you create instabilities in the system. So when we talk about safety in tuning, it's really this idea of augmenting the tuning with guardrails to avoid unsafe configurations, right? So this is very key. And so the problem becomes a constrained optimization problem where parameters have a very careful, safe upper and lower bounds, upper limits that are put in place. And this is really domain specific to Postgres specific for each parameter. And there are memory monitoring guardrails in place, which are constantly monitoring the system. And in real time, the system memory, for example, is being monitored. And the system can automatically quickly revert if it sees that you're using, for example, more than 90% of RAM, which would be considered unsafe, right? So it's not just about machine learning in the wild, it's about machine learning with wrappers around, which we call monitoring guardrails, in this case for memory. And we can then consider another guardrail, for example, on the performance degradation, which early exits the configuration is being run at a given moment in time. This basically means that while the tuning is happening and the tuner is going through all these different configurations, it's also keeping an eye on the memory monitoring, but it's also keeping an eye on the performance degradation. In case there is a performance degradation with a new configuration, it can early exit and automatically go on a configuration that is much more reliable from a performance standpoint. So this is very, very important. And so if we look at what this looks like, before I was talking about the machine learning optimizer like this, but in practice, it's more complex than that, because what you want is the optimizer model, but you also have a safety model, which is a separate machine learning model, which is basically just looking at the safety of this, right? And the guardrails are part of that as well. So meaning that the guardrails are a wrapper around these two models, but the safety model also guides the optimizer model into region of this optimization space that are not risky, right? So the safety model is being trained on the fly, and it gets wiser and wiser to not explore parameters and configurations that are risky for your given use case, okay? So this is very important. And of course, this is a topic by itself. We could create a presentation out of this, but I just wanted to mention that this aspect is extremely important to keep in mind as well. All right, let's talk a little bit about performance. I'm approaching the last part of the presentation where we will just talk a little bit about the performance tuning results. This is an example on Postgres Amazon RDS. And on this very specific instance, the M5 2x large. Here we are optimizing TPCC benchmark, very popular industry standard benchmark. And we have on the x-axis, we have the time in terms of tuning iterations. You can count from 1 to 21 iterations is about 2 hours in total. So this whole axis is about 2 hours. And on the y-axis, we have performance in transactions per second. So in this case, higher the better, because it's transactions per second. And so the tuner here, the auto tuner, has been instructed to optimize transactions per second. So the red line here is the RDS M5 2x large instance that is running TPCC, and it performs at 850 transactions per second. Now, if we double the instance, and we go on M5 for X large, you see that you double the performance, which is great. This doesn't happen all the time, but in this case, for TPCC, you double the size of the instance, you literally double the performance roughly, right? And you see that this lines are flat. Of course, there is a lot of noise. I'm not showing the noise in this plot, but the system is not being changed, meaning that the RDS gives you a configuration. It's always the same. It doesn't change over time, right? And that's why they're flat. But you can see that the blue curve, it's radically different. This is the dbTune curve, and dbTune is running on the small instance, the M5 to X large. And what's happening here is that dbTune explored the optimization space. It looks inside the real-time metrics and automatically adjusts the configuration of the server in a way that it eventually converges into this high-performing area. And you see that the results are as good as the large instance, if not even better. And so dbTune on the small instance can perform as well as the large instance. And this, of course, has some advantages. So on the smaller instance type, it can achieve the level of performance that you have on twice the instance size, right? So if you look at the financial aspect of this, I think it's very interesting. So the hardware on the small instance is a 4-core machine. You see that the large instance is double the size. The RAM is the same, double the size, the disk as well. And so the instance cost is this, the disk cost is this. If you add these two numbers, you get the total cost per year of this instance, $17,000 versus $8,600 for the small instance, right? So this basically means that with dbTune, what you can do is to run on the small instance and save in the process $8,600 per year on just one instance. Okay, so if you tune your instance, you're basically optimizing the cost of your instance by $8,000 per year on one instance. And of course, this means that if you have a large fleet, and very often large companies, they have tens and hundreds, even thousands of RDS instances. Here, that basically means that you take this $8,000 per year and you multiply it by the number of instances, and you can very quickly go in the multi-million-dollar range. So very, very large savings in terms of cost optimization, I should say. Okay. There is this very nice article by Andrews in Norwich, which talks about the over-provisioning issue with the cloud infrastructure and companies out there. So it's very interesting. Go check it out if you're curious to learn more about this. All right. Let's go on a journey of learning a little more about performance results and how much performance is on the table. This plot I really like because it introduces 3 additional benchmarks. Before I was talking about TPCC, here I'm talking about resource stressor, TPCH, and opinions. These again are benchmarks. You can easily download them from the internet. So the first bar is the Postgres in blue, is the Postgres configuration default without tuning. You see, for example, for a resource stressor, and again, this is query runtime milliseconds, so here lower the better. You can see, for example, that the resource stressor runs at 10 milliseconds, TPCH runs at 1,750 milliseconds, and opinions at 5 milliseconds, okay? The green is this approach that I mentioned before, where you only restart once in a maintenance window. You set shared buffers at 25%, and then you just use reload only and tuning, right? So you're tuning automatically, and you are setting shared buffers at 25% in a maintenance window. And what you see is that there is a big jump from this to this, and from this to this, there's a decent jump as well, and there's a massive jump as well in opinions from here to here. So resource stress went from 10 milliseconds to about 2 milliseconds. So there is a 5x improvement in performance. For opinions, very similar, from 5 milliseconds to 1 millisecond. It's again, 5x improvement in performance. The other aspect of this is that if you perform a full tuning, including the restart option that we mentioned before, then you can still squeeze some additional performance. For example, you see though that in some cases the performance improvement is not as massive. So the red one here from the green, you can squeeze some additional performance, especially in TPCH where the performance is noticeable. It's maybe 20% better, but in some other cases it's more moderate, and in some cases it's actually really small. So even the one restart can lead you a long way, and the reload only is actually a very viable solution for tuning. All right, so I will give a final example. So the ones that I was giving before were on performance benchmarks that are downloadable from the internet. But here I wanted to also show a real world application of this. This is a use case study with one anonymized customer of ours. The environment is a 16-core CPU, 32 gigabytes of RAM, an on-prem instance on PG15. This has been manually tuned before. This is the primary instance, and this was manually tuned by an expert DBA, and then it was tuned on top of that with dbtune. And what you can see here is that the first configuration, which is the baseline, performed over here at and then dbtune has tried a number of configurations until it found this green configuration here, which is a 2.5x improvement in performance from the baseline. And these are the parameters that have been changed from these values to these values. So we could have a full talk explaining what happened here between these parameters and these parameters. But you can see some of the changes in terms of, for example, the BG rider and the random page cost, for example, and other things. Okay. But what is interesting here in this example is that db2 was able to improve the performance by 2.5x from a manually tuned instance, which is, I think, a really impressive improvement in performance, right? And this is because the optimization space is very, very complex, and there are always things that you may miss if you're doing manual tuning. Okay, so this is a production example that I like. Of course, we could bring many more of this type. This is something that we observe in production systems quite regularly. So I think this is an example that kind of makes the point for that. There is a publicly available use case study by Stormatics. This was done independently from us as well. And the performance improvement from Postgres default was 13x, which is really impressive. But most importantly, there is another example of manual tuning versus dbtune, and there is a 2.2x improvement in performance in this blog post that is basically the manual tuner versus dbtune. dbtune was still able to do a 2x improvement in performance, a little bit similar to what we've seen here in this production system where the 2.5x. So this has been kind of confirmed as well in that blog post study. There is another blog post by Frank Pachot. I really like this one as well, so go check it out. Those are all independent studies of dbtune, and there is a lot to be learned from these reads. All right, so I want to now wrap this up. I just wanted to talk a little bit about the limitations and notes on AI agents for Postgres tuning. The first thing I'd like to mention is that auto-tuning for cloud providers, we've seen that the APIs of the major cloud providers is pretty flexible and comprehensive, meaning that we can basically tune everything we want. But there are some issues sometimes where some parameters are not exposed, and we would like to tune more than what they expose. So we'd really like to invite all the cloud providers to really make an API that is expansive in terms of and comprehensive in terms of the parameters that can be tuned. Second point is that now that we are approaching this AI agents era, the agentic world, where all these AI agents perform many tasks, and one of them can be performance tuning for Postgres. I think this idea of model context protocol, or MCP, may be quite useful because an agent can actually ask something like the dbtune agent to automatically tune the Postgres instance, and MCP is just the right framework for that, where the MCP protocol really defines the way the agents can interconnect and communicate. Another important point that I would like to make is that performance improvements are somewhat ill-defined. There is workload shifts during the day, daytime versus nighttime workloads, and so on. And so there must be some sort of agreement between the user and the agent on what to optimize. And this is something we will be talking more in the future. We've been working a lot on this approach, which we dubbed workload fingerprint. The workload fingerprint approach, I think, is a way to basically make the user and agent agree on what are the things to optimize, so that then we can scientifically and in a very structured way measure performance in a way that then you can improve over the baseline, and both the user and the agent agree that there is an improvement that is quantifiable and measurable. So the workload fingerprint, I will not talk very much about this in this talk, but stay tuned and no pun intended. Stay tuned, and you will learn more about this workload fingerprint in future presentation of ours. And there is this, of course, this limitation of restarts versus reloads. I think the good news, as I said before, is that shared buffers will be dynamic very soon in future PG releases. So this problem will not be a problem anymore. But for max part worker processes, for example, this is a parameter that is not dynamic. And I didn't see any sign in the Postgres community to tackle this and change this. So these are two things that I think it would be important to keep in mind. Sorry. The last slide on conclusions, but mainly this question of user psychology and society readiness level for Postgres agents. I like to bring up this example of Waymo cars, autonomous driving cars, right? So everybody has been probably seeing this developing over the last 15 years or so. And this is really the idea of taking a person from point A to point B autonomously, right? So if you call it Waymo car in San Francisco or in other cities that have this type of technology, you basically say, Waymo, take me from the Mission District, which is a neighborhood in San Francisco, to Dogpatch, which is another neighborhood in San Francisco, right? So you can basically say, well, take me from point A to point B, and then you sit and you just do something on your phone or just watch, you look at the window and relax. And this just does it for you. In a very similar fashion, what's happening here with technologies like dbTune is really this idea of taking your system from untuned to tuned in an autonomous fashion, right? So you just basically allow the AI agent to perform this autonomously, and you just basically can watch it if you want, maybe stop if you want, or revert back or do things like that from an interface. But pretty much you just basically watch, drink a coffee or something, and you just basically watch this thing being tuned until you get to point B, which is tuned system, which I think is a very good analogy with Waymo. One of the things that it's important to remember is that running a Postgres production system is very challenging, and this idea of putting your Postgres production system in the hands of a software agent is, of course, a little interesting, and perhaps brings some questions and some fears maybe for database administrators. But let's remember that Waymo took 15 years. Okay, so 15 years ago, maybe 5 years ago even, if someone would tell me, we're in San Francisco, let's just take a Waymo car, I would probably say, I'm not sure, well, I would probably take a Uber. But today, Waymos are literally a tourist attraction, and every person that goes to San Francisco now calls a Waymo. It's a super safe way to move around. So it took 15 years, but they got there, and this is a fully autonomous system. It's a super complex system, but it's fully autonomous. It's much more safe to driving your car by yourself, and we believe that the same thing will happen with AI agents for Postgres, and we're already seeing this happening. So there has already been a shift in user psychology for the last 2 years, where we see many more customers now really being comfortable with running dbTune in production systems. It's less of a problem in 2025 than it was in 2023. So I think this is quite interesting. And as an example, in the Postgres community, we have the genetic query optimization, or Gecko, which is something that was released in Postgres in 1996. This is a super old Postgres release. And this was at that time, the state of the art of AI technology, right? So these genetic algorithms were the state of the art in the 90s. And we've seen that the Postgres community has been really open to this already back in the 90s, where they introduced this piece of technology in Postgres. So I think this is quite interesting. And the last point I want to make on this is that there is a thing called technology adoption life cycle. This is how it looks like. So very often when there's a new technology that is quite disruptive, like the one that we described in this talk, very often it starts with the innovators, the technologists, the people really like new technology and like to try it, like to use it in the real world right away, and don't want to wait, right? Then there are the early adopters, and these people have a real pain, a real problem, and they're ready to take a little risk to make it happen and solve the pain. And then there is the early majority and the late majority and the laggards. The laggards are basically these folks that they will only do it when all their friends have done it and they've seen it a million times, and now the technology is so ready that there is nothing that can happen to you, and you just adopt it. And so these are called the laggards. And I believe that in the last couple of years we really moved from the innovators to the early adopters. And so in terms of Postgres automatic tuning, auto tuning, this is very exciting because we are already in a stage of early adopters, and I personally believe that we are very close to crossing what is called the chasm, this moment where the technology basically becomes mainstream, and this becomes an early majority type of adoption from early adopters. So I would love to talk to you in the audience and ask where do you sit in this spectrum of users and adopters, if you are in the early adopter side of things, or maybe you would like to wait a little later until other friends of yours have used this before you start to use it as well. But that's a very interesting kind of user psychology and society readiness level question that I'm quite passionate about. The last thing I want to say is that I will be I will be a guest in an event at PGDA Lowland on September 12th in Rotterdam, where there will be a debate style discussion on auto tuning. I will be debating, of course, pro auto tuning, and please come to the event if you're curious to learn more about this. And there is a very interesting panel recording on YouTube that you can see from PGConf India, where a number of AI experts, including me, I was part of the panel with Bruce and Dennis and a bunch of other Postgres folks. We were discussing AI and Postgres. I think if you are curious, please go ahead and check those references. I added the panel discussion that I just mentioned here and a few other links if you want to learn more about this type of topics. Okay, so this is all I have for today. Thank you very much for listening, and really looking forward to connecting with you and answering some of your questions.
Thank you very much, Luigi. I had one question for you in the chat. If you can take it, can auto tuning fully replace the manual tuning?
So I will stop the recording here. Stop the sharing. So that you can see my face a little better. The question is, can you replace entirely auto tuning? Okay, so this is really what we aim for. Our vision is that auto tuning should be replaced. It's too hard, it's error prone, it takes a lot of time, and we really start to see signals that we can automate that. From a technology standpoint, there's been a lot of progress in research in machine learning models, but also Postgres readiness level for this type of plug and play machine learning models on top of Postgres. So I personally believe that that's possible. We are in the journey of making it happen. And it's really up to you if you want to support this effort by adopting this technology as an early adopter instead of waiting until the very end when everybody else has adopted it. So I would invite you to try it out, because you will really see that it can be automated, at least to some extent today. And we are expanding the scope until we will be able to cover pretty much all the other areas as well.
Thank you. And there is one more question in the chat.
The other questions. Can you share? Could you share some pointers to start with for a new folk like me, who is a Postgres DBA and wants to build a tool for their pain points? Okay, so that's a great question. There is a webpage on the DBTune website, which is really perfect for that, to start to learn about this. This is Imansu, I think, that is asking this question. So I will post very briefly. I will post this link where it's called the DBTune Academy, and it's a 2-hour long training that you can follow step by step. And there is also a practical tutorial that allows you to, and posting this here in the chat, it's really kind of step by step where you can go and learn from the basics to how to actually run it directly yourself by installing a Postgres instance on a synthetic workload like the one that we have shown in this presentation, and then going through the tuning. DBTune has a free tier, so you can go ahead and use the free tier up to 3 instances. You can tune them, so you don't need to pay anything to do this. And then maybe once you run it in a synthetic workload, you can also plug it in your production system and tune a couple of instances in the real world. Any other questions? I see some other messages over here.
No,
but I think we have answered most of the questions.
are there any questions? Okay, thank you. Thank you so much. Thank you to all our wonderful speakers for their insightful talks. We learned a lot and we look forward to the next one. See you all again soon.